Imagine a universe where time and space stretch infinitely, housing secrets waiting to be uncovered. The cosmos is not just a backdrop, it's a dynamic domain brimming with unfathomable mysteries. From the expansive galaxies swirling with stars to the tantalizing prospects of extraterrestrial life, each cosmic phenomenon challenges our understanding of existence. As we journey through intriguing celestial bodies, exploring the wonders of our solar system, we will delve into the unseen forces that shape the fabric of reality. What drives this universe? The Big Bang Theory is a foundational concept in cosmology that explains the origins of our universe. It proposes that approximately 13.8 billion years ago, all the matter and energy that constitutes the cosmos was concentrated in an incredibly hot and dense state. This singularity underwent a rapid expansion known as the Big Bang, which marked the beginning of space and time as we understand them. As the universe expanded, it cooled, allowing for the formation of subatomic particles and later atoms. In the first few minutes after this explosive event, the universe experienced a brief period of nuclear fusion, giving rise to the lightest elements, primarily hydrogen, helium, and a trace of lithium. Over millions of years, these atoms gathered under gravity to form galaxies, stars, and eventually planets. Our own Earth, along with the Milky Way galaxy, is a product of this gradual cosmic evolution. The evidence supporting the Big Bang Theory is extensive. Observations of cosmic microwave background radiation, a remnant heat from the early universe, provide a snapshot of the cosmos when it was just about 400,000 years old. Additionally, scientists observe galaxies moving away from us in all directions, a phenomenon known as redshift, indicating that the universe is still expanding, just as it was after the initial explosion. Importantly, the Big Bang Theory is not just a model of how the universe began. It serves as a framework for understanding its ongoing development. By studying cosmic phenomena from the formation of stars to the behavior of different galaxies, researchers continue to refine our understanding of how the universe behaves over time, helping us to appreciate the vastness and complexity of the cosmos we inhabit. Measuring the immense distances between galaxies is one of the fundamental challenges in astronomy, and scientists have developed several ingenious methods to do just that. One of the most reliable techniques involves the use of light, particularly through a phenomenon known as redshift. As galaxies move away from us, the light they emit shifts to longer, redder wavelengths. By analyzing this redshift, scientists can determine how fast a galaxy is receding, which provides a crucial clue about its distance from Earth. Another essential tool in this cosmic toolkit is the use of standard candles. One of the most famous examples of a standard candle is a specific type of exploding star known as a supernova, particularly the type called Type Ia supernova. These explosions have a consistent brightness, allowing astronomers to gauge their distance based on how dim they appear from Earth. Because these supernovae can be seen across vast stretches of space, they serve as invaluable markers for measuring the distances to far-off galaxies. In addition to these techniques, scientists employ the cosmic distance ladder approach. This is a hierarchical method that combines different measurement techniques for various ranges of distances. For example, parallax, which involves observing a nearby star from two different points in Earth's orbit, is effective for measuring proximity. This foundational knowledge rolls up into broader techniques, including the use of redshift and standard candles to measure further distances. Ultimately, the distances between galaxies can be staggering, often spanning millions or billions of light years. Yet, through the clever application of light, physics, and careful observation, scientists continue to map the cosmos, providing us with a deeper understanding of our universe's structure and its expansive nature. Each measurement builds a larger picture that not only illuminates the universe, but also our place within it. Black holes are among the most fascinating and enigmatic objects in the universe, playing a pivotal role in its structure and evolution. At their core, black holes are regions of space-time where gravity is so intense that nothing, not even light, can escape their grasp. This powerful influence allows them to serve as anchors in galaxies, helping to hold together the vast cosmic structures we observe today. In many ways, black holes are the osmosis of galaxies. Supermassive black holes, often found at the centers of galaxies, can weigh millions or even billions of times more than our Sun. These colossal entities exert a gravitational pull that can affect star formation, orbital dynamics, and even the distribution of dark matter around them. As gas and dust spiral towards a black hole, they create an accretion disk, which heats up and emits X-rays, revealing the presence of these hidden giants. Moreover, black holes contribute significantly to the life cycle of a galaxy. When they consume matter, they release tremendous energy, which can influence the surrounding environment. This energy can regulate star formation by heating up nearby gas or generating outflows that sweep new material away. In this way, black holes can sculpt the galaxies they inhabit, impacting their growth and evolution for billions of years. Interestingly, as much as they shape their surroundings, black holes can also encourage the creation of new stars. The complex interplay of gravity and energy from actively feeding black holes gives rise to dense regions in their vicinity, fostering the conditions necessary for star formation. Thus, black holes are not just cosmic endpoints. They are also central players in the ongoing story of the universe, driving both destruction and creation in the grand tapestry of space-time. Cosmic events such as supernovae play a pivotal role in shaping the evolution of galaxies. These spectacular explosions occur when stars with significant mass exhaust their nuclear fuel, leading to their catastrophic collapse and subsequent detonation. In the aftermath of such an explosion, vast quantities of material are ejected into the surrounding space. This ejected material is rich in heavy elements, many of which are critical for building planets, life, and even new stars. As supernovae shatter the quiet of space, they create shock waves that can compress nearby clouds of gas and dust. This compression can trigger a new wave of star formation, injecting energy into the interstellar medium and rejuvenating regions that may have been dormant. Think of it as the universe's way of recycling elements and fostering the birth of new stars. Without this continual cycle of explosion and rebirth, galaxies would gradually diminish as their matter becomes locked away in dead stars and unformed gas clouds. Moreover, the heavy elements produced by supernovae contribute to the chemical complexity of galaxies. Elements like carbon, oxygen, and iron, forged in the hearts of dying stars, eventually find their way into new stars and planetary systems. This enriching process is essential for creating planets with diverse atmospheres and eventually the conditions necessary for life as we know it. Therefore, each supernova serves not just as an ending, but as a crucial ingredient in the cosmic recipe for growth and diversity in the universe. Supernovae also influence the gravitational dynamics of galaxies. The energy released during these events can alter the motion of stars and gas within a galaxy. In some cases, they can even propel material away from galaxies at high speeds, contributing to what is known as galactic winds. These winds can affect star formation rates, the distribution of matter, and even the overall structure of the galaxy itself. Thus, supernovae are not merely fleeting moments in the timeline of the cosmos. They are fundamental forces in the grand tapestry of galactic evolution. Dark energy is one of the most intriguing and mysterious components of our universe. It is thought to make up about 70% of the total energy content of the cosmos. Unlike ordinary matter and dark matter, which interact through gravity and can be detected through light and other forms of radiation, dark energy does not emit any detectable radiation. This makes it incredibly elusive and thus difficult for scientists to study. Its presence, however, is inferred from the effects it has on the structure and expansion of the universe. The universe is not only expanding, but this expansion is also accelerating. That acceleration is attributed to dark energy. Think of the universe as a balloon being blown up. The surface of the balloon represents the fabric of space itself, and as the balloon expands, galaxies move away from each other. Dark energy acts like a repulsive force that pushes against the attractive force of gravity, causing this expansion to speed up. Without dark energy, we would expect the gravitational effects of matter to slow down the expansion over time. In observations made in the late 20th century, astronomers discovered that distant supernovae were fainter than expected, indicating they were farther away than they should be if the expansion were slowing down. This revelation led to the conclusion that a force was driving this accelerated expansion, which we now call dark energy. Though we may not fully understand what it is, its effect is undeniable, reshaping our view of the universe and its fate. Ongoing research aims to unveil the true nature of dark energy and its potential implications. Some theories explore the possibility that dark energy could change over time, varying its effects as the universe evolves. Understanding dark energy not only addresses fundamental questions about the universe's expansion, but also our own place within this vast, ever-expanding cosmos. Cosmic microwave background radiation, often called CMB, is the faint glow that fills the universe and is a key piece of evidence for the Big Bang theory. To detect and study this radiation, scientists use specialized telescopes and instruments designed to observe in the microwave part of the electromagnetic spectrum. These instruments can pick up the incredibly weak signals that the CMB emits, which has been traveling through space for nearly 14 billion years since the universe cooled enough for light to escape its dense, hot origin. One of the most famous missions to study CMB was the Wilkinson Microwave Anisotropy Probe, or WMAP. Launched in 2001, WMAP mapped the temperature fluctuations in the CMB across the entire sky. Scientists analyzed this data to learn more about the early universe, including its composition and the rate of expansion. These temperature variations can tell us about the distribution of matter and energy in the universe, shedding light on how galaxies and large-scale structures formed over time. More recently, the Planck satellite further enhanced our understanding of the CMB. It provided even more precise measurements of the radiation, allowing researchers to delve deeper into questions regarding the universe's age, shape, and overall content. Planck's detailed observations not only confirmed many aspects of the Big Bang theory, but also hinted at intriguing phenomena, such as the universe's mysterious dark matter and dark energy. As scientists continue to refine their techniques and develop new observational technologies, the study of the cosmic microwave background will undoubtedly unveil more secrets of our universe. Each measurement adds a puzzle piece, helping us piece together the grand narrative of cosmic evolution and our place within it. Redshift is a fundamental concept in cosmology that reveals critical information about the movement of galaxies in our universe. At its core, redshift occurs when a light source moves away from an observer, causing the light to stretch into longer wavelengths. This phenomenon can be likened to the sound of a train passing by, where the sound waves compress as it approaches and stretch as it moves away. When we observe distant galaxies, the light they emit is redshifted, indicating that they are receding from us. This shifting of light toward the red end of the spectrum is not just a curious quirk of physics. It provides vital evidence for the expansion of the universe. The American astronomer Edwin Hubble was instrumental in this discovery during the early 20th century. By measuring the redshift of various galaxies, Hubble found a direct correlation between their distances from Earth and their speeds of recession. This observation led to the formulation of Hubble's law, which essentially states that the farther away a galaxy is, the faster it is moving away from us. The implications of redshift extend beyond simply measuring distances. It also enables astronomers to explore the history of the universe itself. The degree of redshift observed in galaxies can be used to estimate how long the light has been traveling to reach us. This means that when we look at distant galaxies, we are not only seeing them as they are now, but also as they were billions of years ago. This ability to peer back in time sheds light on the early stages of cosmic evolution, helping us to understand how galaxies formed and evolved. Moreover, redshift serves as a crucial tool for uncovering the mysterious influence of dark energy, which is thought to be driving the accelerated expansion of the universe. By examining the redshifts of light from supernovae and other celestial phenomena, scientists can glean insights into the forces shaping our cosmos, helping us to understand how galaxies formed and evolved. Moreover, redshift serves as a crucial tool for uncovering the mysterious influence of dark energy, which is thought to be driving the accelerated expansion of the universe. By examining the redshifts of light from supernovae and other celestial phenomena, scientists can glean insights into the forces shaping our cosmos. As a dynamic and essential concept in cosmology, redshift continues to unravel the complexities of our universe and enhance our understanding of its vastness and age. Quasars, short for quasi-stellar objects, are some of the most luminous and energetic phenomena in the universe. Discovered in the 1960s, these objects resemble stars in their light emissions, but they are actually supermassive black holes actively consuming material in the centers of distant galaxies. As matter spirals into these black holes, it heats up due to immense gravitational forces, producing intense radiation that can outshine entire galaxies. This incredible brightness makes quasars visible even from billions of light years away. What sets quasars apart is their role as cosmic beacons, illuminating the early universe. Because they are found at great distances, looking at quasars allows astronomers to observe light emitted when the universe was much younger, sometimes just a few 100 million years after the Big Bang. This makes them invaluable for studying the conditions and composition of the universe during its infancy. By analyzing the light we receive from quasars, scientists can learn about the formation and evolution of galaxies, stars, and even the intergalactic medium. The study of quasars has also provided critical insights into the expansion of the universe. The redshift of their light reveals that the universe is continually expanding, and it can help estimate its rate of expansion. This information contributes to our understanding of cosmic phenomena such as dark energy, which is believed to be driving this accelerated expansion. Quasars serve as markers in the vast cosmic landscape, allowing researchers to trace the evolution of the universe over billions of years. Quasars are not just fascinating objects in their own right, they are key to unlocking the secrets of the early universe. By studying these bright beacons, astronomers can gather crucial data that sheds light on the formation and growth of galaxies, the origins of cosmic structures, and the underlying mechanics of the cosmos itself. The insights gained from quasars fuel our quest to understand the very fabric of the universe. The discovery of the cosmic web represents a monumental shift in our understanding of the universe. For decades, scientists believed that galaxies were distributed more or less randomly throughout space. However, new observations have revealed a grand tapestry of matter stretching across the cosmos, with galaxies and clusters forming along vast filaments that resemble the structure of a web. This cosmic web is composed of dark matter and baryonic matter, illustrating a complex network of both visible and invisible structures that govern the formation of galaxies. The cosmic web introduces a layer of organization to what was once perceived as a chaotic expanse. Scientists have identified that the filaments of the web are lined with galaxies, while empty regions correspond to cosmic voids. These voids, often hundreds of millions of light-years across, emphasize emptiness in contrast to the densely populated filaments. This interconnected structure not only dictates the behavior of galaxies, but also plays a crucial role in the evolution of the universe itself, influencing galaxy formation, movement, and even the distribution of dark energy. Moreover, the cosmic web alters our perception of cosmic history. It suggests that galaxies are not isolated entities merely floating in space, but instead are tied into a larger framework. This interconnectedness drives home the point that the universe is a dynamic, ever-changing system where the movement of one galaxy can affect its neighbors and where the flow of dark matter shapes the gravitational landscape. Understanding the cosmic web invites us to ponder profound questions about the universe's large-scale structure. It challenges cosmologists to unite the forces of gravity, dark energy, and the mystery of dark matter in a cohesive model that explains not just where galaxies are found, but how they came to exist within this intricate cosmic architecture. As astronomical techniques improve, we can look forward to more revelations about the structures that hold our universe together and how they impact the very fabric of reality. As we explore the ultimate fate of the universe, we encounter theories that delve into the future of everything we know and understand. One of the most widely discussed concepts is the Big Freeze, which suggests that as the universe continues to expand, it will cool down over time. This expansion is driven by dark energy, an enigmatic force theorized to constitute a significant portion of the universe. In this scenario, galaxies move away from each other, and eventually, stars will burn out, leaving behind a dark and cold cosmos. In contrast to the Big Freeze, there exists the theory known as the Big Crunch. This concept posits that the universe's expansion could halt at some point, leading to a gravitational pull that causes everything to collapse into a singularity. This would essentially reverse the Big Bang, creating a climactic finish where all matter and energy converge back into an infinitely dense point. The fate of the universe through the lens of a Big Crunch paints a more dramatic conclusion than the slow, fading entropy predicted by a Big Freeze. Another intriguing possibility is the Big Rip. According to this theory, the accelerated expansion of the universe caused by dark energy could intensify over time, leading to a point where galaxies, stars, planets, and even atoms are pulled apart. This scenario suggests a catastrophic end where the very fabric of space-time is torn asunder, leaving a thin, empty void where our universe once thrived. This catastrophic conclusion forces scientists to consider not just the future of cosmic structures, but also the fundamental forces at play. Lastly, there is the concept of post-biological existence. As the universe continues to evolve, some theorists suggest that advanced civilizations might harness energy on a cosmic scale, potentially transcending physical forms or utilizing cosmic resources in unprecedented ways. This speculative idea invites us to consider not just the end of the universe, but the transformative capabilities and survival strategies of intelligent life that may still exist in the distant future. Each of these theories highlights the continuous quest for understanding, reminding us of the mysteries still lurking at the edges of our knowledge. Dark matter is an elusive and mysterious component of our universe, comprising about 27% of its total mass and energy. Unlike regular matter, which makes up the stars, planets, and even ourselves, dark matter does not emit, absorb, or reflect light, making it invisible and detectable only through its gravitational influence on visible matter. This makes it one of the most intriguing subjects in modern astrophysics. Regular matter, made up of atoms, is responsible for the ordinary physical objects we interact with in our daily lives. It has mass and takes up space, allowing us to see and touch it. In contrast, dark matter interacts with other matter only through gravity. This subtle interaction is crucial for understanding the structure of galaxies and the universe as a whole. For instance, observations of galaxies show that they contain far more mass than can be accounted for by the visible stars and gas alone. This discrepancy suggests the presence of dark matter, exerting a gravitational pull that keeps galaxies from flying apart. Evidence for dark matter primarily comes from the behavior of galaxies and larger cosmic structures. Astronomers have studied the rotation rates of galaxies, where the outer edges rotate much faster than expected based on the visible mass. Additionally, the way galaxy clusters bend light around them, known as gravitational lensing, provides further insight into the unseen mass surrounding these clusters, attributed to dark matter. Scientists are still striving to understand the nature of dark matter fully. Various candidates have been proposed, including weakly interacting massive particles, or WIMPs and axions, but none have been definitively detected. Exploring dark matter adds depth to our comprehension of the universe, suggesting that most of it remains hidden, waiting for future discoveries that may reveal its secrets and further illuminate our understanding of cosmic reality. Gravitational waves are ripples in the fabric of spacetime, caused by some of the most violent and energetic processes in the universe. When two enormous celestial bodies, such as black holes or neutron stars, collide or spiral toward each other, they create disturbances in spacetime that generate these waves. Detecting gravitational waves allows scientists to observe cosmic events that are often invisible through traditional methods like optical telescopes. The unfolding discovery of gravitational waves began in 2015 with the groundbreaking observations made by the Laser Interferometer Gravitational Wave Observatory, commonly known as LIGO. LIGO's sensitive instruments can pick up the minuscule distortions caused by passing gravitational waves, stretching and squeezing space itself. Such measurements provide a new way to study phenomena that are otherwise hidden, offering insights into the merging of black holes and the explosive deaths of stars. By analyzing the signals generated by these waves, researchers can probe the characteristics of the cosmic events that produce them. For instance, the specific chirp pattern of a merged black hole event reveals information about the masses of the black holes involved and their distance from Earth. This adds a dimension to our understanding of the universe, complementary to what we learn from electromagnetic radiation, like light. Moreover, gravitational wave astronomy opens the door to studying events that occurred in the early universe. These waves carry information that can provide clues about the conditions prevailing just moments after the Big Bang. As technology continues to improve and more detectors come online, the field of gravitational wave astronomy promises to revolutionize our understanding of the cosmos, unveiling secrets that have long eluded researchers. Antimatter holds a profound significance in our understanding of the universe, acting as a key to some of its most fundamental mysteries. Essentially, antimatter is the counterpart to ordinary matter. For every particle in our world, there exists an antiparticle that shares the same mass but carries the opposite charge. This means that when a particle and its corresponding antiparticle collide, they annihilate each other, producing energy in the form of high-energy photons or gamma rays. This remarkable process not only illuminates the nature of energy and mass, but also reveals the intricate balance that sustains our universe. Beyond its theoretical importance, antimatter also has practical applications that impact contemporary science and technology. For instance, in medical imaging, positron emission tomography, or PET scans, utilizes a type of antimatter known as positrons to detect diseases, including cancer. Moreover, antimatter is crucial in the field of particle physics, where it helps researchers probe the underlying principles of the universe by recreating conditions similar to those just after the Big Bang. This exploration helps scientists investigate why ordinary matter seems to dominate today, despite the expectation that matter and antimatter should have been created in equal quantities. The study of antimatter further fuels our quest for answers regarding the origins and fate of the cosmos. One of the pivotal questions in cosmology is why our universe favors matter over antimatter. This imbalance hints at fundamental asymmetries that might reveal new physics beyond our current models. Understanding this phenomenon could lead to groundbreaking discoveries about the universe's structure, its eventual fate, and the fundamental forces that govern all interactions. Antimatter is not just a theoretical curiosity, it is woven into the very fabric of the universe. It serves as a reminder that the cosmos is a complex tapestry of opposites, where the dance between matter and antimatter continues to shape the world we perceive and the laws that govern it. As researchers delve deeper into the intricacies of antimatter, we may soon uncover more secrets that the universe has yet to reveal. astronomers have developed an impressive array of techniques to study exoplanets, those distant worlds orbiting stars outside our solar system. One of the most successful methods is the transit method, where scientists observe the light from a star. If a planet passes in front of the star, it temporarily blocks some of the light, causing a brief and detectable dip in brightness. This method not only confirms the existence of a planet, but also allows astronomers to determine its size and orbital period. Another critical technique is the radial velocity method. Here, astronomers measure the wobble of a star caused by the gravitational pull of an orbiting planet. These tiny shifts in the star's position affect the light spectrum we observe, revealing the planet's mass and distance from the star. Both methods complement each other, painting a richer picture of the kinds of environments exoplanets might inhabit. Once potential exoplanets are identified, especially those within the habitable zone, the region around a star where conditions might be right for liquid water, scientists turn to spectroscopy. This technique involves analyzing the light that passes through an exoplanet's atmosphere during a transit. By examining the spectral fingerprints of various elements and molecules, astronomers can gather clues about the planet's atmosphere and its potential to support life. Detection of gases like oxygen, methane, or water vapor raises intriguing questions about the possibility of habitability. As we advance our observational technologies, such as powerful space telescopes and ground-based observatories, the search for exoplanets continues to yield fascinating discoveries. Each new finding brings us closer to understanding not just the composition of these distant worlds, but also the potential for life beyond Earth. With thousands of exoplanets confirmed and many more on the horizon, we are witnessing an exciting era in the quest to find our cosmic neighbors. Gravity, one of the fundamental forces of nature, behaves in ways that often intrigue and puzzle scientists. One of the most significant anomalies comes from observations of galaxies. When astronomers study the rotation curves of these massive systems, they find something unexpected. The outer regions of galaxies spin much faster than predicted based on the visible matter present. This discrepancy leads to the suggestion of an unseen component, which we now refer to as dark matter. Moreover, the effects of gravity appear to change when we look at larger cosmic structures. For instance, the behavior of galaxy clusters, particularly how they gravitationally bind themselves, raises further questions. The mass needed to hold these clusters together cannot solely be accounted for by the visible matter. This anomaly deepens the mystery surrounding dark matter, indicating that about 25% of the universe might be made up of this elusive substance. Another intriguing aspect is linked to the expansion of the universe, particularly its acceleration. In the late 20th century, observations revealed that galaxies are receding from us at an accelerating pace. This unexpected behavior challenges the traditional understanding of gravity and suggests the influence of dark energy, which composes nearly 70% of the universe. The nature of dark energy remains one of the most profound mysteries in cosmology, indicating that our understanding of gravity may be far from complete. Additionally, on smaller scales, gravity behaves oddly in certain environments. Extreme conditions near black holes and neutron stars may not adhere to the conventional rules set by general relativity. The quest to reconcile gravity with quantum mechanics further complicates our grasp of this force. These anomalies collectively suggest that gravity is more complex than previously thought, propelling scientists to rethink established theories and push the boundaries of our understanding of the universe. Quantum entanglement presents a fascinating possibility for the future of space exploration by potentially revolutionizing the way we communicate and process information across vast distances. At its core, quantum entanglement describes a phenomenon where pairs or groups of particles become linked in such a way that the state of one particle can instantaneously affect the state of another, no matter how far apart they are. This could lead to the development of communication systems that are instantaneous, overcoming the significant delay caused by the vast emptiness of space. Imagine spacecraft on distant missions sending back data with no lag time. This could transform our relationship with distances in space. For example, if two spacecraft were entangled, any information sent from one could arrive at the other in real time. This would not only enhance the efficiency of interstellar communications, but could also allow for more precise control over missions as they venture deeper into the cosmos. Moreover, entanglement could play a crucial role in quantum computing, which harnesses the principles of quantum mechanics to perform calculations at incredible speeds. With advancements in this technology, we could analyze enormous sets of astronomical data much more quickly. This capability would be invaluable for tasks such as deciphering complex cosmic phenomena, thus accelerating our understanding of the universe. Finally, the implications of quantum entanglement extend beyond just communication and computation. The foundation of scientific inquiry often rests on collaboration and data sharing. By utilizing entangled particles, researchers could develop a more interconnected global network for exploring the cosmos. The result would not just be enhanced communication, but a shared consciousness in our quest to uncover the mysteries of space, paving the way for a new era of exploration and discovery. Neutrinos are fascinating particles that play a critical role in our understanding of the universe. These nearly massless particles, which barely interact with matter, are produced in vast quantities during nuclear reactions in stars, during supernova explosions, and from cosmic ray interactions in the atmosphere. This makes them abundant, as well as uniquely capable of providing insights into cosmic processes that are otherwise hidden from telescopes or other detectors. One of the most compelling aspects of neutrinos is their role in the study of supernovae. When a massive star collapses, it releases an enormous amount of energy, and in this process, it emits an astonishing number of neutrinos. In fact, a supernova can generate more neutrinos in the first few seconds than the Sun will produce in its entire lifetime. By detecting these neutrinos, scientists can gain crucial information regarding the dynamics of the explosion and the behavior of matter under extreme conditions. This helps us understand the life cycles of stars and the mechanisms of stellar death. Neutrinos are also thought to be key players in cosmic mysteries such as the origins of dark matter. While much is still unknown, certain theoretical models suggest that a specific type of neutrino, known as a sterile neutrino, could account for some of the invisible mass we observe. This could help bridge the gap between our understanding of visible matter and the mysterious dark components of the universe that seem to outweigh it by a significant margin. Moreover, scientists are leveraging neutrinos to probe some of the most profound questions in physics. Experiments that detect neutrinos from the Sun and from other cosmic sources have led to important discoveries related to neutrino oscillation, revealing that these particles can change types as they travel through space. This phenomenon has implications not only for our understanding of particle physics, but also for the very fabric of the universe itself. Neutron stars are extraordinary celestial objects that arise from the remnants of massive stars after they undergo a supernova explosion. When a supernova occurs, the outer layers of the star are blown away, leaving behind a dense core. This core collapses under gravity, compressing protons and electrons together to form neutrons, which gives rise to the neutron star's unique composition. In fact, a neutron star is so densely packed that just a sugar cube-sized amount of its material would weigh about the same as all of humanity combined. What makes these stars even stranger is their incredibly strong gravitational fields and magnetic fields. A neutron star's gravity is about 2 billion times stronger than that of Earth. This immense force alters the fabric of space and time around the star, creating an environment that challenges our understanding of physics. The gravitational pull is so powerful that it can warp light, allowing observers to witness phenomena such as gravitational lensing, where light from other stars is bent around the neutron star. Additionally, neutron stars are known for their rapid rotation. After the supernova explosion, they often spin at astonishing rates, sometimes rotating hundreds of times per second. This rapid rotation, combined with their strong magnetic fields, produces beams of radiation that sweep across space, much like a lighthouse. When these beams point toward Earth, we observe pulsars, highly regular pulses of radiation that act as cosmic clocks, offering insights into the structure of the universe and fundamental physics. Moreover, the density and conditions in neutron stars provide a unique laboratory for studying matter under extreme circumstances. Inside these stars, we encounter states of matter that cannot be replicated on Earth, such as superfluidity and superconductivity. Neutron stars challenge our understanding of matter, gravity, and the very laws of physics, making them some of the most fascinating objects in our universe and offering glimpses into its most enigmatic processes. The life cycle of stars is a fascinating journey that begins in stellar nurseries, where clouds of gas and dust collapse under their own gravity to form protostars. As these protostars heat up, they eventually ignite nuclear fusion in their cores, marking the beginning of the main sequence phase. This is where stars like our Sun spend the majority of their lives, steadily fusing hydrogen into helium. As a star exhausts its hydrogen fuel, it undergoes dramatic changes. For medium-sized stars, like the Sun, this leads to the red giant phase. In this stage, the core contracts and heats up, allowing the star to begin fusing helium into heavier elements. The outer layers expand significantly, dominating the celestial landscape and causing the star to glow in a deeper red hue. This transformation marks a stunning visual change, as these red giants become some of the largest stars in the universe, often ballooning to several times their original size. Eventually, the star exhausts its helium and other heavier fuels, reaching the end stages of its life. For medium-sized stars, the outer layers become unstable and are shed, creating a beautiful nebula. What remains is the core, which becomes a white dwarf. This small, dense remnant is no longer undergoing fusion and instead gradually cools and fades over billions of years. The white dwarf is a fascinating endpoint, shining faintly from the residual heat of its formation. In the grand cycle of stellar evolution, both red giants and white dwarfs play crucial roles. They contribute to the recycling of matter in the universe. The material expelled during the red giant phase enriches the interstellar medium, providing the building blocks for future generations of stars and planets. Meanwhile, white dwarfs, once they cool completely, contribute their elements back to the cosmos, continuing the cycle of life in our universe. This interconnected process illustrates the dynamic nature of cosmic evolution, revealing how stars live, evolve, and ultimately return to the galactic tapestry. Rogue planets are fascinating celestial bodies that stand apart in our galaxy. Unlike the planets that orbit stars, rogue planets drift through the cosmos without a steady home. Their unique status raises many intriguing questions about their origins and characteristics. Some astronomers estimate there are more rogue planets than stars in our galaxy, suggesting that our universe may be teeming with these mysterious wanderers. One of the most striking features of rogue planets is their diverse range of sizes and compositions. Some may be rocky, resembling Earth or Mars, while others could be gas giants, similar to Jupiter or Saturn. Despite their differences, what unites them is the lack of a parent star, which dramatically influences their atmospheric conditions and surface temperatures. Without the heat and light from a star, many of these planets are incredibly cold, some reaching frigid temperatures that make them inhospitable to life as we know it. Rogue planets can also exhibit unexpected features due to their isolated environment. For instance, they may possess their own atmospheres, albeit thin and composed of various gases. Some scientists speculate that certain rogue planets could harbor subsurface oceans, kept from freezing by internal heat produced from radioactive decay or leftover heat from their formation. This possibility opens up exciting discussions about the potential for life in places once thought uninhabitable. The journey of rogue planets often begins as regular planets that are ejected from their solar systems, often due to gravitational interactions with larger bodies. These encounters can be violent, flinging planets into the vast emptiness of space. The fact that these planets wander alone makes them all the more intriguing, pushing scientists to explore how they fit into our understanding of planet formation and evolution in the universe. As we uncover more about these elusive worlds, we continue to expand our knowledge of what exists beyond the familiar confines of our solar system. Brown dwarfs occupy a fascinating space in the celestial hierarchy, acting as intriguing bridge objects between planets and stars. Essentially, these cosmic bodies are often described as failed stars. However, the term provides only a partial picture of their unique characteristics. Brown dwarfs form in a similar way to stars, collapsing from gas and dust in molecular clouds. But unlike stars, they never gather enough mass to ignite the fusion of hydrogen at their cores. Typically, brown dwarfs have masses ranging from about 13 to 70 times that of Jupiter, placing them in a category distinct from both stars and gas giant planets. While a star shines brightly due to the nuclear fusion reactions perpetually occurring within it, brown dwarfs do not possess the requisite mass to sustain such reactions for a prolonged duration. Instead, they primarily generate energy through the fusion of deuterium and lithium, elements that have much lower atomic weights compared to hydrogen. This process, however, is short-lived, allowing these objects to cool and fade over time. The low temperatures and luminosities of brown dwarfs make them quite elusive compared to their brighter stellar neighbors. They are often described as being dim and cool compared to stars, which can make them hard to detect, even with powerful telescopes. This faintness leads scientists to compare them with giant planets, especially given that some brown dwarfs are similar in composition to gas giants, composed mainly of hydrogen and helium. This connection deepens our understanding of planetary formation and evolution, as studies show that these dwarf bodies can share various characteristics with the planets orbiting their host stars. Brown dwarfs also contribute insights into the conditions that exist in early cosmic history. Pioneering observations of these objects reveal information about the formation of stars and planetary systems, providing a context for understanding our own solar system. In this way, brown dwarfs serve not only as curious objects in the night sky, but also as key players in the broader narrative of the universe, linking the worlds of planets and stars in a continuous and intriguing cosmic tapestry. Pulsars, those remarkable rotating neutron stars that emit beams of electromagnetic radiation, hold secrets that illuminate the cosmos, particularly the early universe. By studying the light they emit, scientists can glean valuable insights about the conditions and events that shaped the universe shortly after the Big Bang. Pulsars are born from the remnants of massive stars that have undergone supernova explosions, which means their existence is inherently tied to the life cycles of these stellar giants. One fascinating aspect of pulsars is their incredible precision. Some pulsars spin hundreds of times per second, emitting regular pulses of radiation that can be predicted with impressive accuracy. This regularity allows astronomers to use them as cosmic clocks. As scientists observe these clocks over time, they can detect tiny variations in their rotation rates caused by gravitational waves or distortions in space-time, phenomena that can provide clues about the density and distribution of matter in the early universe. Furthermore, pulsars can probe the environment of the early universe through their interactions with cosmic background radiation. As they emit their beams, they can reveal the effects of dark matter and dark energy, substances that make up most of the universe's mass-energy content, yet remain largely mysterious. The study of pulsars sheds light on how these elements might have influenced the evolution of the universe, from its rapid inflationary phase to the formation of the first stars and galaxies. Pulsars act as timekeepers and messengers from the early universe, revealing details about its fundamental structure and the forces that shaped it. As our understanding of these extraordinary objects deepens, so too does our grasp of the universe's origins, pushing the boundaries of human knowledge ever further into the cosmic past. Comets are often described as the ancient relics of our solar system, holding vital clues about its early history. Formed in the cold outer regions, these icy bodies are believed to contain original materials from the time of the solar system's formation, approximately 4.6 billion years ago. As they travel through the cosmos, comets carry with them primordial material that can help scientists piece together the conditions that prevailed during those formative years. When a comet approaches the Sun, it begins to show its magnificent display. Ice within the comet vaporizes, releasing gas and dust that creates a glowing halo, or coma, and often a spectacular tail. This process allows scientists to study the composition of these materials in detail. By analyzing the gases and dust released, researchers can gain insights into the building blocks of the solar system, including organic molecules and other compounds that could provide clues about the origins of life. Moreover, the orbits of comets can offer a glimpse into the gravitational influences of massive bodies in the solar system. For instance, some comets are long-period comets, originating from the Oort cloud, a distant, spherical shell surrounding our solar system. The trajectories of these comets can reveal the gravitational forces exerted by distant stars and the potential perturbations that shape their paths. This knowledge deepens our understanding of dynamical processes in our celestial neighborhood. By studying comets, scientists can unlock stories etched in ice and gas, offering a direct connection to the solar system's infancy. These fascinating visitors not only illuminate the past, but also help refine our understanding of the processes that shaped our planetary home, enhancing our grasp of cosmic history and the emergence of life on Earth. The study of extreme exoplanets can reveal crucial insights into the diverse processes of planetary formation and evolution. These exoplanets, some of which are located in hostile environments or exhibit unusual characteristics, challenge our previous assumptions about how planets form around stars. For example, gas giants discovered close to their parent stars, known as hot Jupiters, indicate that planetary migration plays a significant role in the shaping of planetary systems. They form far out in the cooler regions of a solar system, then migrate inward due to gravitational interactions, providing clues about the dynamics in these celestial neighborhoods. As researchers examine planets with extreme temperatures, unusual atmospheric compositions, or orbiting in binary star systems, they begin to understand the wide range of outcomes that can arise during the planet formation process. Planets like lava worlds, where molten rock covers the surface, suggest conditions that can arise from very close proximity to their stars. Such extremes highlight how the composition and structure of a planet is directly influenced by its formation environment and the energy it receives from its sun. Moreover, these unusual worlds prompt scientists to rethink the building blocks of planetary systems. The presence of specific chemical compounds in the atmospheres of extreme exoplanets can reveal the processes that occur both during and after formation. For instance, analyzing the atmospheres of some hot Jupiters has shown the presence of water vapor, carbon monoxide, and even exotic elements like titanium, painting a broader picture of what materials are available in various solar systems. Extreme exoplanets are natural laboratories that help astronomers refine their models of planetary formation. Each new discovery not only expands our understanding of how planets come to be, but also prepares us for the complex nature of planetary systems beyond our solar neighborhood. By studying these peculiar worlds, we sharpen our understanding of the remarkable variety of planetary systems and the underlying processes that govern their formation and behavior. Studying the atmosphere of distant planets, particularly those outside our solar system, is a fascinating endeavor that combines advanced technology and innovative scientific techniques. Astronomers utilize a method called spectroscopy, which analyzes the light that passes through or reflects off a planet's atmosphere. When a planet passes in front of its host star, some of the star's light filters through the atmosphere before reaching Earth. This process creates a unique fingerprint, as different elements and molecules absorb specific wavelengths of light. By examining these fingerprints, scientists can determine the atmospheric composition of these distant worlds. This technique not only reveals the gases present, but also gives insight into the planet's temperature, pressure, and potentially even seasonal changes. For instance, if a planet shows signs of gases like oxygen, methane, or carbon dioxide, It may suggest chemical processes that could indicate the presence of life. The presence of these gases raises intriguing questions about biological activity, since many of them are typically associated with living organisms on Earth. To refine these observations, astronomers utilize powerful telescopes, both on Earth and in space. Instruments like the Hubble Space Telescope and the upcoming James Webb Space Telescope are designed to unveil the mysteries of distant exoplanets by providing crucial data on their atmospheres. Researchers are also developing specialized techniques to minimize disruptions from starlight, allowing for clearer observations of these distant worlds. As technology advances, our ability to study the atmospheres of distant planets will only improve. This work is crucial for our search for extraterrestrial life, as understanding the conditions on these planets can help us identify which ones may have the potential to support life. With each discovery, we inch closer to answering one of humanity's most profound questions. Are we alone in the universe? Super-Earths are a class of exoplanets that are larger than our own Earth, but significantly smaller than gas giants like Neptune and Uranus. Typically, they fall within a size range of about 1 to 10 times the mass of Earth. What makes these planets particularly captivating is their potential to host conditions suitable for life and their diverse geological and atmospheric possibilities. One of the intriguing aspects of super-Earths is their varied compositions. Some may have rocky surfaces similar to Earth, while others could be enveloped in thick atmospheres rich in hydrogen or helium. This diversity raises questions about the formation and evolution of these planets, as they can offer scientists a glimpse into other planetary systems and how they interact with their stars. Another fascinating feature is their ability to exist within what is called the habitable zone, the region around a star where conditions might allow liquid water to persist on a planet's surface. The presence of water is a key ingredient for life as we know it. The exploration of super-Earths could uncover worlds with climates and conditions that are surprisingly similar to our own or radically different, pushing the boundaries of our understanding of life's potential in the universe. In recent years, discoveries made by missions like the Kepler Space Telescope have identified a multitude of super-Earths. These findings have ignited the interest of astronomers and astrobiologists alike, as they continue to speculate about the possibilities that these planets might present for future exploration and the search for extraterrestrial life. Each new discovery challenges our perceptions and inspires new questions about what lies beyond our solar system. Binary star systems present a fascinating challenge to our understanding of celestial mechanics, the branch of astronomy that deals with the movements and interactions of celestial bodies. In a binary system, two stars orbit a common center of mass, which fundamentally shifts the dynamics we observe in the universe. These systems can vary greatly, with some having stars of similar size and mass, while others may feature one massive star paired with a much smaller companion. The presence of two stars complicates the gravitational interactions, introducing intricate orbital patterns that are far more complex than those seen in single-star systems. One of the most intriguing aspects of binary systems is the phenomenon of gravitational interactions, which can lead to various outcomes. For instance, through a process called mass transfer, one star may draw material from its companion, altering their individual life cycles and affecting their evolutionary paths. This interaction can result in dramatic transformations, such as novas or even supernova, challenging traditional life cycle models of stars. The study of these interactions provides insights into the longevity and final remnants of stars, including neutron stars and black holes. Moreover, binary stars allow astronomers to determine stellar masses with remarkable accuracy, something that is not easily achievable with isolated stars. By observing the orbital motion of the stars, scientists can apply Kepler's laws of planetary motion to derive their masses. This has immense implications because understanding mass is crucial for deciphering a star's life cycle and the physics governing its formation. It essentially allows us to test theories of stellar evolution in ways that single stars cannot. Finally, the study of binary systems expands our knowledge of the universe's structure and formation history. As these stars influence each other through their gravitational pull, they can serve as cosmic laboratories, revealing details about the nature of dark matter, galaxy dynamics, and the expansion of the universe itself. Binary star systems act as both puzzles and windows into the vast, intricate workings of celestial mechanics, continuously reshaping our understanding of the cosmos. Mars has long been a captivating focus of scientific inquiry, harboring mysteries that continue to ignite the imaginations of researchers around the globe. One of the most significant enigmas is the presence of water, past and perhaps present, on the planet's surface. Evidence from rovers and orbiters suggests that liquid water once flowed through its valleys and now hides in polar ice caps and possibly even beneath its surface. The question of whether microbial life could have existed in those ancient rivers, or if any extant life forms persist deep underground, remains tantalizing. Another captivating mystery is Mars's atmosphere and climate history. Once thought to be a rich and warm environment, today Mars is a cold desert world with a thin atmosphere composed mainly of carbon dioxide. Scientists are diligently studying how this transition occurred. Understanding the processes that led to the loss of a thick atmosphere may unlock clues not just about Mars, but also about climate evolution on Earth and the solar system's history as a whole. The planet's geology offers its own set of puzzles. Massive volcanoes, such as Olympus Mons, and colossal canyon systems like Valles Marineris raise profound questions about the geological forces at work on Mars. What caused these features to form, and why does Mars exhibit such stark contrasts from Earth? The study of Martian geology could reveal insights into the planet's volcanic activity and tectonic processes, providing a deeper understanding of planetary formation and evolution. Lastly, the possibility of human exploration pushes the boundaries of our imagination. Questions swirl around how we would sustain human life on Mars, what technologies we might need, and, crucially, whether we would be the first living organisms to set foot on its surface. As we anticipate future missions and the potential for colonization, each discovery drapes a new layer of intrigue over the red planet, making Mars a focus of hope, challenge, and curiosity for generations to come. Neptune and Uranus, often referred to as ice giants, stand apart from the other planets in our solar system due to their distinct compositions and atmospheric characteristics. Unlike the gas giants Jupiter and Saturn, which are primarily made up of hydrogen and helium, these giants contain a higher proportion of what are known as volatiles. These volatiles include substances like water, ammonia, and methane, leading to the rich, icy nature of their interiors. One of the most striking differences is found in their atmospheres. While Jupiter boasts a swirling expanse of colorful clouds, Neptune and Uranus display a more muted palette dominated by shades of blue and green. This coloration is largely a result of methane gas, which absorbs red light and reflects blue light back to space. Additionally, Neptune is known for its dynamic and active atmosphere, featuring some of the strongest winds recorded in the solar system, while Uranus is more tranquil and coated with a haze of clouds. Another fascinating element of these ice giants is their unique axial tilt. Uranus is unique among the planets as it rotates on its side, with an axial tilt of approximately 98 degrees. This unusual orientation leads to extreme seasonal variations and has sparked curiosity about its formation history. Neptune, on the other hand, maintains a more conventional axial tilt but has a similarly complex climate that results in storms and shifts over time. Finally, the interior structures of Neptune and Uranus are quite different from the terrestrial planets like Earth and Mars. Beneath their thick atmospheres, they are believed to possess a mantle composed of ice and other volatiles, surrounding a rocky core. This icy layer defines their classification as ice giants and highlights the diversity of planet types within our solar system, reminding us of the many mysteries that still await our discovery in the cosmic expanse. Jupiter's Great Red Spot is a colossal storm, one of the most iconic features in our solar system. Spanning about 1.5 times the diameter of Earth, this storm has raged for at least 300 years, showcasing the planet's dynamic atmosphere. The distinctive reddish hue of the storm tantalizes scientists, hinting at complex chemical reactions occurring in the upper atmosphere. These reactions involve compounds like phosphine and ammonium hydrosulfide, which contribute to its striking color. What makes this storm particularly fascinating is its persistence. Unlike storms on Earth that cycle through rapid lifespans, the Great Red Spot benefits from an entirely different atmospheric structure. Jupiter is predominantly made of hydrogen and helium, with powerful winds and a significant lack of landmass to disrupt storm patterns. The planet's fast rotation creates a nature of turbulent airflow that sustains the storm, allowing it to maintain its structure even in the face of ongoing energy dynamics. Moreover, the Great Red Spot is not static. Instead, it undergoes changes and fluctuations in size and intensity. Over the past few decades, observations suggest that the storm is shrinking, leading to questions about its future. This is part of the broader dynamics of Jupiter's atmosphere, where the interaction of different jet streams and thermal conditions continually reshapes weather patterns, adding layers of complexity to this extraordinary phenomenon. Scientists are keenly observing these developments, as understanding the Great Red Spot could provide insights into atmospheric processes not only on Jupiter but also on other gas giants and even Earth itself. This unique storm serves as a natural laboratory, revealing the intricacies of planetary atmospheres and reminding us of the incredible diversity of weather systems that exist beyond our home planet. Saturn's ring system is one of the most captivating features in our solar system. These magnificent rings, composed of countless particles ranging from tiny ice grains to massive chunks of rock, offer valuable insights into planetary formation. The structure and composition of Saturn's rings suggest that they are remnants from the early solar system, perhaps the remains of moons that were torn apart by gravity or material that never coalesced into a planet. The rings also present a unique opportunity to study processes that are thought to happen during planetary formation. As ice and rock particles collide and interact with each other, they can merge or shatter. This ongoing activity is similar to the processes that formed the planets, providing a snapshot of the chaotic environment of the early solar system. By studying these interactions, scientists can better understand how larger bodies might have formed from smaller ones in the protoplanetary disk. Moreover, the rings reveal the influence of Saturn's many moons. The gravitational pulls of these moons create structure within the rings, carving out gaps and forming waves. This dynamic interaction showcases how celestial bodies can shape their environments. It's a process that likely played a significant role in the history of our solar system, illuminating how planets and their systems evolve over billions of years. Lastly, by examining the composition of the ring particles, scientists gain insight into the materials available during the solar system's formation. The presence of water ice in the rings suggests that these particles originated in a cold region, while the diverse range of other elements hints at a rich and varied environment. This evidence supports theories about how planets like Saturn created their unique characteristics, giving us a clearer picture of how our cosmic neighborhood came to be. Recent discoveries about Venus have sparked renewed interest in our neighboring planet, particularly in the context of studying climate change. Scientists have found that Venus, often called Earth's twin due to its similar size and composition, has a thick atmosphere composed mainly of carbon dioxide, leading to an extreme greenhouse effect. However, the recent detection of phosphine gas in the atmosphere raised eyebrows because, on Earth, phosphine is associated with biological processes. While the origin of this gas on Venus is still debated, it opens up intriguing possibilities for understanding atmospheric processes and climate dynamics. Another significant finding involves the cloud layers of Venus. These clouds are composed of droplets of sulfuric acid, but recent observations have suggested that they could harbor strange chemical processes that were previously unknown. Such discoveries could help scientists better understand how different elements interact in extreme conditions. Insights gained from studying Venus's atmospheric chemistry may inform models of planetary climate systems, not just for our planet, but for potentially habitable exoplanets as well. Moreover, the study of Venus's geological features, like vast plateaus and potential volcanic activity, adds further depth to our understanding. By comparing these geological processes with those on Earth, researchers hope to uncover how different planetary environments respond to similar climatic forces. Such comparisons can help shed light on the broader implications of climate change and highlight the importance of planetary stewardship as we grapple with our own climate crisis. As our exploration of Venus progresses, particularly with future missions planned for the coming years, we stand on the brink of significant revelations. Each discovery draws parallels to Earth's own climatic challenges, reminding us that studying other planets can enhance our understanding of our own environment. Thus, Venus not only captivates our imagination, but also serves as a laboratory for studying global climate change, offering valuable lessons for sustaining life on Earth. The asteroid belt, situated between Mars and Jupiter, represents a fascinating window into the early solar system. Formed from the remnants of material that never coalesced into a planet, these rocky bodies can tell us a great deal about the past processes that shaped our cosmic neighborhood. Essentially, they are leftovers from the solar system's formation, dating back around 4.5 billion years. Studying these asteroids helps scientists understand the conditions and materials present during the solar system's infancy. This zone is primarily composed of various types of rock and metal, some of which may contain organic compounds or even water ice, hinting at the chemical precursors to life. The diversity of asteroids offers a glimpse into the processes that influence the formation of planets and provided critical building blocks for life. In addition, the asteroid belt acts as a sort of time capsule, preserving features that have long since been lost on Earth and other planets. Due to their smaller size, asteroids tend to experience much less geological activity compared to larger celestial bodies, which means they retain the impact scars of billions of years of space weathering. Analyzing these impacts allows astrobiologists and planetary scientists to reconstruct the historical environment of the solar system, highlighting where asteroids came from and how they interacted with the planets nearby. Moreover, missions like NASA's Dawn, which studied the dwarf planet Ceres and the asteroid Vesta, have uncovered detailed information about these fragments. The data collected helps fill gaps in our understanding of planetary formation, migration, and the characteristics of early solar materials. Thus, the asteroid belt is not just an area filled with rocks, it is a treasure trove of information that deepens our appreciation for the cosmic history that led to the formation of our own planet and its ecosystems. The moons of Jupiter and Saturn have emerged as critical players in the search for extraterrestrial life. Specifically, Europa, one of Jupiter's largest moons, and Enceladus, a moon of Saturn, have captured the interest of scientists due to compelling evidence suggesting they might harbor conditions suitable for life. Beneath their icy surfaces lie vast oceans of liquid water, a fundamental ingredient for life as we know it. Europa features a surface of ice that covers an ocean deep beneath. The moon has a thin atmosphere rich in oxygen, and there are suggestions that the ocean may come into contact with Europa's rocky mantle below. This interaction could create a chemistry akin to that found in Earth's deep-sea hydrothermal vents, environments that support diverse ecosystems far from sunlight. The presence of potential energy sources alongside water raises the tantalizing possibility that microbial life could exist in Europa's depths. Enceladus, on the other hand, presents a different but equally fascinating scenario. This small moon is known for its geysers that erupt plumes of water vapor and organic molecules into space. These plumes indicate that there are hydrothermal activities occurring on the ocean floor, suggesting an ongoing geological process that creates the conditions necessary for life. The interplay of water, heat, and organic compounds points toward a potentially vibrant environment where life could thrive. Studying these moons not only enhances our understanding of where life could exist beyond Earth, but also challenges our definitions of habitability. By investigating the extremes of our solar system and the diverse environments that could support life, we open our minds to the vast possibilities of life beyond our planet, fundamentally reshaping our understanding of biology and the cosmos. Through missions planned to explore these icy worlds further, we inch closer to answering one of humanity's most profound questions. Are we alone in the universe? Solar eclipses are remarkable celestial events that offer unique opportunities to deepen our understanding of both the Sun and the Moon. During a total solar eclipse, the Moon completely obscures the Sun, casting a shadow on Earth and allowing us to observe the Sun's corona, which is its outer atmosphere. This crown of plasma, normally invisible due to the brightness of the Sun, reveals crucial information about solar activity and structure. By studying the corona during eclipses, scientists can gather insights on solar radiation and its impact on Earth. The temperatures in the corona are astonishing, reaching millions of degrees, far hotter than the Sun's surface. Understanding this temperature disparity is vital for comprehending the dynamics of solar wind and magnetic fields, which play significant roles in space weather phenomena. These phenomena can disrupt satellite communications and even power grids on Earth, making this knowledge all the more essential. Moreover, solar eclipses also contribute to our knowledge of the Moon's orbit and its relationship with Earth. Observing the way the Moon moves in front of the Sun helps refine our measurements of its distance from Earth. This, in turn, allows for improved models of gravitational interactions between the Earth, Moon, and other celestial bodies, leading to a better understanding of tidal forces and their effects on our planet. Solar eclipses serve as natural laboratories for scientists. They not only illuminate the mysteries surrounding the Sun's corona and its energetic activities, but also enhance our understanding of the complex dance between the Earth and the Moon. Each eclipse, although fleeting, is packed with potential discoveries, reminding us of the interconnectedness of these celestial bodies and the ever-expanding universe that surrounds us. Mercury, the closest planet to the Sun, reveals a treasure trove of secrets that challenge our understanding of planetary formation and evolution. This small, rocky world is shrouded in mystery due to its extreme temperatures and unique surface conditions. It experiences the most significant temperature fluctuations in the solar system, with daytime highs soaring to about 800 degrees Fahrenheit, while nights can plunge to near -330 degrees Fahrenheit. Such extremes arise from its thin atmosphere, which cannot retain heat, creating a stark contrast that our other planetary neighbors don't experience. One of the most captivating secrets of Mercury lies in its surface features. Scanning images from the Messenger spacecraft showcases a landscape scarred by craters, ridges, and giant cliffs known as Labat Scarps. These formations suggest that Mercury has undergone significant geological activity long after its formation. The discovery of these cliffs indicates that the planet experienced contraction as it cooled, shrinking its surface over billions of years. Mercury is a time capsule, preserving evidence of ancient processes that shaped our solar system, making it a crucial piece of the cosmic puzzle. Furthermore, the planet's magnetic field adds another layer of intrigue. Despite being only a third of the size of Earth, Mercury possesses a magnetic field about 1% the strength of Earth's. This magnetic field is a mystery. It appears to be generated by a molten outer core, suggesting that Mercury's interior may still be partially active. The presence of a magnetic field raises questions about the planet's history and its ability to sustain such a phenomenon despite its small size and proximity to the Sun. Mercury also reveals insights into the solar wind and how it interacts with planetary bodies. With no substantial atmosphere to shield it, the planet is constantly bombarded by solar particles. Observations show that this interaction may have contributed to the formation of a surface layer rich in volatile elements like sodium, giving it a peculiar and highly reflective quality. This fleeting dance between Mercury and the Sun not only shapes its surface, but also hints at broader implications regarding the atmospheres and surfaces of planets throughout our solar system. Through Mercury, we begin to unlock the various ways celestial bodies interact with their stellar environment, providing a deeper understanding of planetary life cycles. Dwarf planets, particularly Pluto, continue to captivate scientists and the public alike for a multitude of reasons. One of the primary factors is their unique status within our solar system. For many years, Pluto was considered the ninth planet, only to be reclassified as a dwarf planet in 2006. This shift sparked debates about what defines a planet and how we categorize astronomical bodies, leading to a reconsideration of our solar system's structure. Pluto, along with other dwarf planets like Eris and Haumea, offers a glimpse into the early solar system. These celestial bodies are thought to be remnants from its formation, preserving clues about the conditions and processes that shaped our cosmic neighborhood billions of years ago. The presence of various types of ice and complex organic molecules on their surfaces further fuels scientific interest. The mysteries locked within their icy crusts could tell us more about the evolution of planets and, by extension, the potential for life in our universe. The exploration of Pluto took a giant leap forward with NASA's New Horizons mission in 2015. This spacecraft provided the first close-up images of Pluto and revealed a rich tapestry of geological diversity, including vast plains, towering mountains, and what appeared to be glaciers made of nitrogen. Such discoveries challenge our understanding of small celestial bodies and their dynamic processes, raising questions about the potential for atmospheric activity and even cryovolcanism. Moreover, some researchers are actively studying the orbital dynamics of dwarf planets and their moons. For example, Pluto's moon Charon shows intriguing signs that enhance our understanding of binary systems in space. Each new finding opens new avenues for research, illustrating how much we still have to learn about these distant worlds. As dwarf planets continue to be studied, they remind us that the universe is full of surprises, sparking curiosity and inspiring further exploration. A galaxy is a vast collection of stars, gas, dust, and dark matter, all bound together by gravity. At its core, a galaxy typically has a supermassive black hole, which is surrounded by hundreds of billions of stars. These stars can be arranged in various structures, ranging from spiral arms to elliptical shapes. The Milky Way, our home galaxy, is a prime example of a spiral galaxy, featuring beautiful, sweeping arms that are laden with stars and nebulae. Galaxies come in an astonishing range of sizes and types. The smallest galaxies, known as dwarf galaxies, can contain as few as a few billion stars. In contrast, the largest galaxies, called giant galaxies, may host over 1 trillion stars. In terms of type, galaxies are broadly classified into 3 categories: spiral, elliptical, and irregular. Spiral galaxies, like the Milky Way, have a flat disk and a bulging center. Elliptical galaxies are more rounded and can range from nearly spherical to elongated shapes. Irregular galaxies, as their name suggests, do not have a distinct shape and often appear chaotic. This variety arises from the complex processes of galaxy formation and evolution. Galaxies can merge with one another, leading to the creation of larger structures or altering their shapes drastically. For instance, the collision of 2 spiral galaxies can result in the formation of an elliptical galaxy. Additionally, interactions between galaxies, such as gravitational pulls, can lead to the exchange of stars and gas, influencing their evolution over billions of years. Understanding the characteristics and classifications of galaxies helps astronomers piece together the history of the universe. The patterns we observe in galaxies today offer crucial insights into the fundamental forces that shape our cosmos. By studying these celestial entities, we can glean knowledge about the birth, life, and eventual fate of the universe itself. Spiral galaxies and elliptical galaxies are 2 primary types of galaxies, each with distinct structures and characteristics that define them. Spiral galaxies, like our Milky Way, feature a flat, rotating disk containing stars, gas, and dust, along with a central concentration of stars known as a bulge. This disk often exhibits beautiful spiral arms extending outward, created by the density of stars and the complex interactions of gravity. These arms are home to many young, bright stars, giving spiral galaxies a vibrant appearance. In contrast, elliptical galaxies are generally more rounded and three-dimensional in shape, resembling an elongated or oval sphere. They lack the prominent disk structure and spiral arms found in spiral galaxies. Instead, elliptical galaxies consist of a smooth distribution of older stars, with little to no gas and dust present. As a result, they typically show a more uniform brightness and have a more subdued color palette, usually dominated by red hues. This coloration stems from the population of older stars that reside in these galaxies, which, unlike the young blue stars of spiral galaxies, have exhausted much of their nuclear fuel. The formation processes of these galaxies also differ significantly. Spiral galaxies often grow by accumulating gas and dust, allowing for ongoing star formation. This vibrant activity is sustained by the conservation of angular momentum as material spirals inward. Elliptical galaxies, on the other hand, are generally thought to form from the merger of smaller galaxies, leading to a more stable configuration with minimal new star creation over time. This merger process leads to a dynamic reshaping of stellar orbits, which contributes to the smooth appearance of elliptical galaxies. Moreover, the environments that these galaxies inhabit can also provide clues about their nature. Spiral galaxies are frequently found in richer environments, such as groups or clusters, where interactions and exchanges of materials occur more readily. Elliptical galaxies, however, are more often located in dense galaxy clusters where gravitational interactions have shaped their evolution over billions of years. Understanding these differences not only provides insight into the structure of our universe, but also illuminates the fascinating processes that govern galaxy formation and evolution. Galactic collisions are pivotal events in the vast choreography of the universe. They serve as magnificent demonstrations of cosmic dynamics, showing how galaxies interact and evolve over immense timescales. When two galaxies collide, it is not just a simple merging of objects. It sparks a series of complex processes that can reshape entire galaxies, redistribute stars, gas, and dust, and even trigger new waves of star formation. This phenomenon reveals the interconnectedness of galaxies and their influence on one another, much like a dance where each participant profoundly affects the others. During these encounters, the gravitational forces between the galaxies create spectacular tidal interactions. Imagine two swirling clouds of stars, gas, and dark matter nudging against each other, stretching and pulling as they collide. The gravitational tug-of-war can lead to the creation of elongated tidal tails that trail behind each galaxy, filled with newly formed stars and stellar debris. This is not just chaos, it's a crucial process for galactic evolution, often leading to the birth of new stars and even the formation of new galaxies. Enlighteningly, these cosmic collisions are not isolated events, but rather a common aspect of galactic life. Our own Milky Way is on a collision course with the neighboring Andromeda galaxy. Predicted to occur in about 4 billion years, this encounter will radically alter both galaxies. Over eons, such events can lead to larger structures, like galaxy clusters, forming as smaller groups merge. Therefore, galactic collisions drive the growth and transformation of the universe itself, shaping its structure at grand scales. Beyond their physical consequences, the study of galactic collisions offers insights into the history of galaxies and the evolution of the cosmos. By examining the remnants of these encounters, astronomers can trace the paths that galaxies have taken through time. This helps us understand not just where we come from, but also the fate awaiting our own galaxy and many others. Thus, galactic collisions are not just collisions. They are fundamental events that pulse at the heart of cosmic evolution, weaving together the story of the universe itself. Mapping and categorizing the vast number of galaxies in the universe is one of the most ambitious endeavors in modern astronomy. Scientists employ a combination of powerful telescopes, advanced imaging techniques, and sophisticated data analysis methods to understand the distribution and characteristics of these galaxies. With an estimated 2 trillion galaxies populating the universe, each with its own unique shape, size, and content, this task is akin to cataloging an unfathomable ocean of stars and cosmic structures. One of the initial steps in galaxy mapping involves utilizing ground-based and space-based telescopes which capture light across various wavelengths, from visible to infrared and beyond. These telescopes can observe distant galaxies that emitted light billions of years ago, allowing astronomers to see not just where galaxies are located, but also how they have evolved over cosmic time. Large astronomical surveys, such as the Sloan Digital Sky Survey and the Hubble Space Telescope's legacy fields, have collected vast amounts of data, creating extensive catalogues that detail the shape, brightness, and color of countless galaxies. Once the data is collected, astronomers categorize galaxies based on key characteristics, such as their morphology or structure. The Hubble sequence, for instance, divides galaxies into ellipticals, spirals, and irregulars, allowing researchers to create a clearer picture of their diversity. This morphological classification helps scientists understand the processes that form galaxies and how they interact with their environment. Furthermore, advances in machine learning are beginning to play a vital role in processing and analyzing astronomical data, rapidly identifying and classifying galaxies, which helps keep up with the increasing volume of information being generated. In addition to morphology, astronomers study the environments in which galaxies reside, including clusters, groups, and the vast voids in between. Understanding these contexts can reveal the influence of gravitational interactions and the dark matter that binds galaxies together. As our techniques improve and new telescopes come online, the mapping of galaxies becomes more detailed, shedding light on the complex tapestry of the universe and deepening our understanding of how these cosmic giants fit into the grand story of cosmic evolution. At the heart of nearly every large galaxy, including our own Milky Way, lies a supermassive black hole. These astronomical giants have masses ranging from millions to billions of times that of our Sun. They act as the central engines that have a profound impact on the formation and evolution of galaxies. As supermassive black holes grow, they attract vast amounts of gas, dust, and even stars, creating immense gravitational fields that help shape the structure of the galaxy around them. The presence of a supermassive black hole influences how stars form and cluster in its vicinity. Regions close to the black hole can experience intense gravitational forces, causing material to heat up and emit bright radiation. This energetic output often results in the formation of an active galactic nucleus, where powerful jets of radiation and particles blast out into space. Such activity can carve out cavities in the surrounding interstellar medium, affecting star formation rates in the galaxy. Furthermore, supermassive black holes may play a crucial role in regulating the growth of their host galaxies. When these black holes consume gas and other materials, they can release tremendous amounts of energy. This energy can either stimulate new star formation or, conversely, suppress it by expelling gas from the galaxy. This complex interplay between black holes and their host galaxies showcases the dynamic relationship that shapes their evolution over billions of years. Supermassive black holes are not just cosmic vacuum cleaners. They are key players that shape the very structure and developmental path of galaxies. As we delve deeper into our understanding of these enigmatic entities, we unveil the secrets of galactic formation and evolution on a cosmic scale, profoundly expanding our perspective of the universe we inhabit. Astronomers study the halo and disk components of galaxies using a variety of observational techniques and advanced technologies. One of the most important tools in their arsenal is spectroscopy, which allows scientists to analyze the light emitted or absorbed by objects in space. By breaking down this light into its constituent colors, astronomers can determine the chemical composition, temperature, and motion of stars and gas within the galaxy. In the case of the disk component, which contains most of a galaxy's stars and gas, astronomers often look at the distribution and movements of these stars. Observations of the rotational velocities of stars at different distances from the galactic center reveal crucial information about the mass of the galaxy, including the presence of dark matter. This spiral structure can be mapped out using both optical telescopes and radio observatories, which can detect the cold gas that forms the molecular clouds where new stars are born. On the other hand, studying the halo component is a bit more complex. The halo is a roughly spherical region surrounding the galaxy that contains older stars, globular clusters, and a significant amount of dark matter. To explore this area, astronomers utilize high-resolution imaging techniques and deep-field surveys. These surveys capture light from distant galaxies, allowing astronomers to infer the presence and effects of the halo, as the gravitational pull from the halo affects the motion of neighboring galaxies. Additionally, modern telescopes equipped with specialized instruments can capture faint glows of hot gas and dark matter in the halo. Techniques like gravitational lensing, where the presence of a massive galaxy distorts the light from more distant objects, provide valuable insights into the halo's structure and mass. Through all these methods combined, astronomers can piece together a detailed understanding of how both the halo and disk components contribute to the complex architecture of galaxies. The formation of new stars within galaxies is a profound indicator of cosmic evolution, reflecting the dynamic processes that shape not just individual galaxies, but the universe as a whole. In simple terms, stars are the building blocks of galaxies, and their birth is intricately linked to the conditions present in the cosmos at any given time. By studying how and when stars form, scientists can glean important insights into the history and future of the universe. Stars are born from vast clouds of gas and dust that accumulate in the cold, dark regions of space. When these clouds contract under their own gravity, they heat up, eventually igniting nuclear fusion in their cores. The rate of star formation can vary significantly across different galaxies and epochs, influenced by factors such as the availability of raw materials and external gravitational influences. Observing these variations helps researchers understand the timeline of cosmic history, revealing how galaxies evolve over billions of years. Moreover, the types of stars that form, like massive stars that rapidly evolve and die, or smaller, longer-lived stars, impact the surrounding environment. For instance, massive stars produce intense radiation and supernova explosions, enriching the surrounding gas with heavy elements. This process is crucial, as these elements become the building blocks for future generations of stars and planets, illustrating a cycle of cosmic rebirth. Each new generation of stars tells a story about the conditions that existed during its formation era, contributing to our understanding of the universe's evolving complexity. Watching how new stars emerge within galaxies acts like a cosmic time capsule. It provides clues about the physical processes at play and the evolutionary stages of those galaxies. This not only deepens our appreciation of the intricate dance of matter and energy across the universe, but also lets us glimpse the eventual fate of our own galaxy and the larger cosmic landscape. As we continue to observe and study star formation, we unravel more of the universe's extraordinary narrative. The evolution of galaxies is a captivating journey that unfolds over billions of years. Galaxies begin as clouds of gas and dust in the vast universe, gradually coalescing under the force of gravity. As these particles come together, they ignite the birth of stars, creating a beautiful tapestry of light in the cosmos. This initial phase is just the beginning, as galaxies continue to change and evolve through various processes that shape their structure, size, and composition. One of the most significant factors influencing galactic evolution is the interaction between galaxies. These interactions can occur in various forms, ranging from close encounters to dramatic collisions. When galaxies collide, their gravitational forces can trigger waves of star formation, reshaping their structures. After such events, the galaxies may merge into new, larger entities, giving rise to spectacular elliptical galaxies or more complex spiral shapes. These transformative events can also redistribute gas and dust, fueling new generations of stars. Additionally, the environment surrounding a galaxy plays a critical role in its evolution. Galaxies exist in clusters, groups, or isolation, and their surroundings can affect their rate of star formation and the material available for building new stars. For example, in crowded galaxy clusters, galactic interactions may occur more frequently than in isolation, leading to different evolutionary paths. This dynamic interplay leads to the diversity of galaxy types observed in the universe today, from the majestic spirals to the austere, irregular galaxies. Over time, galaxies also experience changes in their stellar populations. As they age, stars within galaxies evolve, with some eventually becoming supernovae or turning into white dwarfs, neutron stars, or black holes. This continual process influences the chemical composition of the galaxy and the types of future stars that can form. Thus, the story of a galaxy is one of constant evolution, shaped by its interactions, environment, and the life cycle of its stars, leading to the stunning variety we observe in the cosmos. The galactic center of the Milky Way is a hotbed of mystery and intrigue, enticing astronomers and astrophysicists alike. Nestled in the direction of the constellation Sagittarius, this region is home to a supermassive black hole named Sagittarius A star. Though invisible to optical telescopes, its presence is inferred through the astonishing orbits of nearby stars. These stars travel at incredible speeds, revealing that a mass roughly 4 million times that of the Sun is concentrated in a space no larger than our solar system. This observation raises fascinating questions about the formation and evolution of our galaxy. Despite the significant understanding we have gained, multiple enigmas linger. For instance, the exact nature of the material that swirls around Sagittarius, a star, remains uncertain. Is this gas and dust behaving in expected patterns, or are there unforeseen processes influencing their movement? The intense environment near the black hole can emit high-energy radiation, creating a dynamic region that challenges our theories of particle behavior and gravitational physics. Investigating these aspects could unlock new revelations about the very fabric of space and time. Moreover, the galactic center is not just about black holes and high-energy radiation. It hosts a diverse collection of stars, gas clouds, and complex structures known as the nuclear bulge. This hub of activity raises compelling questions about star formation in extreme conditions. How have stars managed to form and survive in such a chaotic environment? Studying their life cycles can provide vital clues to the overall evolution of the galaxy and even help astronomers understand our celestial neighborhood in a broader context. Ultimately, the mysteries of the Milky Way's center are intricately woven into the larger tapestry of cosmology. Delving into these enigmas not only informs our understanding of the Milky Way, but also contributes to our comprehension of galaxies as a whole. As astronomers continue to develop advanced observational technologies, such as powerful radio and infrared telescopes, we may soon uncover answers to these perplexing questions, further illuminating the dark heart of our galaxy. In the vast cosmos, scientists categorize galaxies based on their shapes, sizes, and behaviors. Regular galaxies, such as spiral and elliptical galaxies, exhibit clear and well-defined structures. Spirals have beautiful arms that spiral out from a bright center, while ellipticals range from nearly spherical to elongated shapes. These structures result from millions, sometimes billions, of years of gravitational forces acting in harmony, leading to largely predictable characteristics. On the other hand, peculiar galaxies are a bit of an enigma. They display unusual features that set them apart from their more conventional cousins. These galaxies often appear distorted or irregular due to a variety of factors, such as encounters with other galaxies, gravitational interactions, or extreme cosmic events like supernova explosions. The chaos of these interactions can result in shapes that defy standard categorization, giving peculiar galaxies their distinctive identities. Astronomers employ a combination of visual observation and complex imaging techniques to identify these differences. By analyzing the light emitted or absorbed by the galaxies, they can deduce fundamental properties such as composition, age, and distance. This data can help identify irregularities in structure and behavior, guiding researchers toward understanding the dynamic processes at play. While regular galaxies conform to a recognizable order and pattern, peculiar galaxies symbolize the unpredictable nature of the universe. They invite scientists to explore the underlying forces at work in the cosmos, revealing not only the beauty of diversity among galaxies, but also the fascinating stories that each galaxy holds. Searches for biosignatures beyond Earth are a fascinating amalgamation of cutting-edge technology and planetary science. Scientists begin this monumental task by exploring other celestial bodies within our solar system, focusing on those with conditions that could potentially support life. Locations such as Mars and the icy moons of Jupiter and Saturn, like Europa and Enceladus, are hotbeds of activity, as they harbor subsurface oceans and other promising environments. The search across these extraterrestrial terrains is built upon a multifaceted approach that combines robotic missions, landers, and orbiters. Once these missions reach their targets, the instruments aboard are specifically designed to detect chemical signs of life. Instruments may analyze soil samples, atmospheric gas compositions, or surface materials for organic compounds, which are the building blocks of life as we know it. For instance, missions like the Mars Perseverance rover use advanced technology to examine the Martian soil and atmosphere for traces of ancient microbial life. Scientists have meticulously planned these investigations to ensure that they can differentiate between biological and non-biological processes, an essential aspect when hunting for biosignatures. Beyond our solar system, the search extends to distant exoplanets. Astronomers use powerful telescopes to study the atmospheres of these planets and look for specific gases that could indicate the presence of life. Significant focus is placed on gases like oxygen or methane, which, when found together, could strongly suggest biological activity, as they typically would react with one another and thus need a constant source to persist. The emerging field of astrobiology combines elements from multiple scientific disciplines to analyze these findings, seeking patterns or indicators that point toward the potential for life around distant stars. The quest for biosignatures is not solely about finding life, but also about understanding how life might exist in different forms throughout the universe. Whether it's through the analysis of our neighboring planets or examining the atmospheres of far-off worlds, scientists are piecing together the enigmatic puzzle of life beyond Earth. This ongoing exploration fuels our curiosity and increases our understanding of the vast possibilities that may lie within the cosmos. The Fermi paradox presents an intriguing contradiction within the search for extraterrestrial life. While the universe is vast, ancient, and filled with potentially habitable planets, we have yet to find any definitive evidence of intelligent life beyond Earth. This paradox, named after the physicist Enrico Fermi, raises questions about the likelihood of extraterrestrial civilizations existing and the implications of their apparent absence. One significant implication of the Fermi paradox is the Great Filter hypothesis. This theory suggests that there may be a critical stage in the evolution of life that is incredibly difficult to surpass. This could mean that while microbial life may be common, intelligent civilizations capable of space travel and communication might be exceedingly rare. The Great Filter could occur at various points, potentially before life ever emerges, or after civilizations reach a certain technological threshold, leading to self-destruction through war, environmental degradation, or other catastrophic events. Another consideration is the possibility that advanced civilizations are intentionally avoiding contact with us. This idea is often framed through the zoo hypothesis, which suggests that extraterrestrial societies purposely avoid interfering with our development, observing humanity much like we observe animals in a zoo. This positions humanity as a species still in its infancy when it comes to understanding our place in the universe. In addition, the distances between stars and galaxies, along with the limitations of our current technology, could contribute to the silence of the cosmos. While there are billions of stars and planets, the sheer vastness of space makes communication and exploration a monumental challenge. As we continue to develop and refine our methods of detecting extraterrestrial signals and scanning for biosignatures, we might find that the universe's silence is not a sign of solitude, but rather an indication of the complexity involved in connecting with others in the cosmos. Through continued exploration and discovery, the mysteries of the Fermi paradox could unfold, opening new avenues in our quest for understanding life's place in the universe. Extremophiles are organisms that thrive in environments once thought to be uninhabitable, places characterized by extreme temperature, acidity, salinity, or pressure. Their existence challenges our understanding of life's limitations and opens up exciting possibilities for what we might discover beyond Earth. For instance, organisms that survive in boiling hot springs or in the frozen Arctic tundra demonstrate that life can adapt to conditions we once believed would be lethal. Scientists study extremophiles to understand the biochemical processes that allow these organisms to endure extreme stress. By examining their unique adaptations, we can gain insights into the potential signatures of life in distant worlds. For example, Martian soil may not be hospitable to typical Earth life, yet extremophiles that thrive in high radiation environments could inform our search for similar resilient organisms on Mars. These organisms might give us clues about how life could develop or survive in extreme extraterrestrial environments. Moreover, extremophiles have been found in subglacial lakes in Antarctica and deep-sea hydrothermal vents. These environments are analogous to conditions present on moons like Europa, which has a subsurface ocean beneath its icy shell. By understanding how extremophiles function in such extreme settings, scientists can focus their searches for life on celestial bodies that share similar characteristics. This knowledge enhances our ability to identify biosignatures, indications of life, such as specific chemical compounds or unusual spatial distributions of elements in far-off planets. Ultimately, extremophiles serve not only as models for resilience, but also as a beacon for astrobiology. Their diverse mechanisms for survival underline a fundamental truth. Life is adaptable, and the universe could be teeming with organisms capable of thriving in environments that defy our traditional expectations. As we look outward, these earthbound marvels might just lead us to new discoveries about the universe's secrets and the possibility of finding life beyond our planet. The Drake equation is a fascinating framework developed in the early 1960s by the American astronomer Frank Drake. Its primary purpose is to estimate the number of potential civilizations in our galaxy with which we might be able to communicate. Rather than being a definitive calculation, it serves as a way to stimulate scientific dialogue regarding the factors that influence the development of intelligent life in the universe. At its core, the equation considers several variables that collectively impact the likelihood of extraterrestrial civilizations. These factors include the number of stars born each year in our galaxy, the fraction of those stars that have planetary systems, the average number of planets that could potentially support life, and the probability that life actually arises on those planets. It also takes into account the fraction of planets where life evolves into intelligent beings and the length of time those civilizations are able to communicate. While the Drake equation does not provide a single answer, it invites us to think about the vastness of the universe and the conditions necessary for life. The estimates generated rely heavily on current scientific knowledge, which means they can vary widely as new information becomes available. For instance, as we discover more exoplanets, our understanding of the likelihood of habitable worlds increases, adjusting the equation's outcome. Ultimately, the Drake equation highlights not just the search for extraterrestrial intelligence, but also our curiosity about life's existence beyond Earth. It opens up a larger conversation about our own place in the cosmos, the nature of life's diversity, and the potential for connection with other intelligent beings out there among the stars. With every new technological advancement in space exploration, our quest to answer the ultimate question of whether we are alone continues to evolve. The search for extraterrestrial intelligence, commonly known as SETI, is an ambitious project aimed at uncovering any signs of intelligent life beyond our planet. The core philosophy behind SETI is the notion that if there are other technologically advanced civilizations in the universe, they might be sending out signals, like radio waves, which we could detect. By systematically scanning the skies with powerful telescopes, researchers hope to identify these signals, ultimately answering the timeless question of whether we are alone in the cosmos. One of the key advancements in SETI initiatives is the development of sophisticated algorithms and data analysis techniques. In the past, scientists would manually sift through the vast amounts of data collected from radio telescopes, an incredibly time-consuming task. Today, artificial intelligence and machine learning are revolutionizing this process, enabling researchers to detect patterns and potential signals with greater efficiency. This technological leap allows for a more thorough exploration of the cosmos, increasing the chances of capturing a genuine extraterrestrial communication. In addition to technological advancements, SETI initiatives have fostered global collaboration among scientists from diverse fields. For instance, projects like the Breakthrough Listen initiative gather expertise from astronomy, engineering, and computer science to enhance the search for extraterrestrial signals. The partnerships formed within the scientific community not only broaden the scope of research, but also expedite the understanding of the universe and our place within it, creating a truly interdisciplinary approach to what could be one of humanity's most profound discoveries. Moreover, SETI does not solely focus on auditory signals. Researchers are also exploring other forms of communication, including optical signals using lasers. This expansion of focus means that even if we don't detect traditional radio transmissions, we could still uncover evidence of intelligent life through different means. As humans explore the possibilities of communication across the vastness of space, every breakthrough in SETI advances our understanding of the universe and ignites the imagination about what lies beyond our own world. Recent discoveries on Mars have invigorated scientific discussions about the possibility of life, past or present, on our neighboring planet. One of the most compelling pieces of evidence comes from the discovery of organic molecules in Martian soil samples. These molecules, which are the basic building blocks of life as we know it, were identified by the Curiosity rover. Detecting these organic compounds does not confirm life existed on Mars, but they certainly raise the tantalizing possibility that the chemical precursors to life might be present. In addition to organic molecules, researchers have identified seasonal changes in certain regions of the Martian surface that indicate the presence of liquid water, albeit in very salty forms. Water is crucial for life, and its transient existence on Mars suggests that conditions might have been favorable for life to develop at some point in the distant past. The recurring slope lineae, streaks that appear on slopes during warmer months, are among the most intriguing phenomena linked to water flow on the planet today. Furthermore, geologic findings reveal ancient riverbeds and lakebeds scattered across the Martian landscape. These features suggest that Mars once had a more hospitable environment that could have supported microbial life. The presence of clays and other sedimentary rocks suggests a history of water, which is essential for life as we understand it. As scientists continue to analyze samples returned from Mars missions and further explore the planet using advanced rovers, our understanding of its potential to harbor life expands. The recent Mars missions, including the Perseverance rover equipped with sophisticated laboratory instruments, are not only searching for signs of ancient life, but also active biosignatures in contemporary Martian environments. With the ability to collect and analyze rock and soil samples in extraordinary detail, these missions stand at the forefront of our quest to answer one of humanity's most profound questions. Are we alone in the universe? As we peel back the layers of Mars history, the prospect of discovering microbial life past or present, continues to inspire a new generation of explorers and scientists alike. Studying the atmospheres of exoplanets is a fascinating field that has emerged from advances in technology and our growing understanding of the universe. Scientists employ various methods, primarily focused on the analysis of light. When a star shines its light through an exoplanet's atmosphere during a transit event, when the planet passes in front of its star, some of that light is absorbed by the gases in the atmosphere. This creates a unique fingerprint that signals the presence of different molecules. One of the central tools used in this research is spectroscopy. By analyzing the spectrum of light that filters through the atmosphere, scientists can identify the elemental and molecular composition. For example, if specific markers associated with water vapor, carbon dioxide, or methane appear in the spectrum, it could suggest conditions that might support life. Researchers pay particular attention to gases that on Earth are associated with biological processes, as their presence could indicate potential livability. As technology continues to evolve, instruments like space telescopes are becoming more sophisticated. The James Webb Space Telescope, for instance, offers unprecedented capabilities in investigating these distant worlds. With tools that can detect even the faintest signals from an exoplanet's atmosphere, scientists can probe deeper into their chemical compositions, searching for signatures of habitability or even biosignatures, which are indicators that life may be present. In recent years, the journey to understanding these distant atmospheres has also expanded to involve simulations and models. By comparing observed data with theoretical predictions, researchers can refine their approaches and improve our understanding of the conditions under which life might arise. This dynamic synergy between observation, analysis, and simulation keeps the quest for extraterrestrial life vibrant and bustling with potential discoveries. Each clue from an exoplanet brings us closer to answering one of humanity's biggest questions. Are we alone in the universe? Astrobiology missions play a crucial role in our quest to discover life beyond Earth. These missions combine the disciplines of biology, chemistry, geology, and astronomy to explore the potential for life in diverse environments across the universe. They aim to identify the fundamental building blocks of life and to study the conditions under which life might arise, survive, and thrive. By understanding these processes, scientists can form hypotheses about where we might find extraterrestrial life. One of the primary focuses of astrobiology missions is the exploration of other celestial bodies within our solar system. For instance, Mars missions, like the Perseverance rover, are not only searching for signs of past life, but are also gathering data about the planet's geology and climate. Mars may have once had conditions suitable for life, and examining its surface can provide insights into the history of water essential for life as we know it. Similarly, the icy moons of Jupiter and Saturn, such as Europa and Enceladus, are targets of interest due to their subsurface oceans, which could harbor microbial life. These missions are not limited to our solar system. They also involve studying exoplanets, planets located outside our solar system that orbit other stars. Advanced telescopes, such as the James Webb Space Telescope, are designed to analyze the atmospheres of these distant worlds. By identifying chemical signatures or biosignatures, researchers can assess the potential for life. The detection of certain gases, like oxygen or methane, could indicate biological processes, prompting further exploration. Overall, astrobiology missions are integral to answering one of humanity's most profound questions. Are we alone in the universe? With each mission, we gather more information about life's diversity and resilience, expanding our understanding not only of where to look for life, but also of what life might be like beyond our home planet. These endeavors fuel our curiosity and guide us in the ongoing search for answers among the stars. The quest for technosignatures, signals, or indicators of advanced extraterrestrial civilizations differs substantially from the search for biological evidence of life beyond Earth. While both endeavors aim to understand our place in the universe, they pivot on different concepts of what constitutes a signature of life or intelligence. Searching for biological evidence typically involves identifying the chemical building blocks associated with life, such as organic molecules or microbial activity. This approach often focuses on environments where life might exist, such as subsurface oceans on icy moons or the tantalizing conditions on exoplanets. The goal here is to find direct indicators, like fossils or metabolic byproducts, that suggest life as we know it, or at least life forms that share some characteristics with earthly organisms. In contrast, exploring for technosignatures emphasizes the search for artifacts or signals that imply the presence of intelligent beings. This can mean detecting laser pulses, radio waves, or even physical constructs like megastructures, massive engineering projects that would alter the surrounding celestial environment. The underlying assumption changes. Rather than looking for signs of biological processes, scientists seek evidence of technological activities that would suggest advanced civilizations capable of manipulating energy and resources on a grand scale. Both approaches are a race against the unknown, but they operate under different frameworks and tools. The biological search is often grounded in astrobiology and chemistry, while the hunt for technosignatures draws on fields like astrophysics and engineering. Each path adds a piece to the grand puzzle of life and intelligence in the cosmos, offering new perspectives that widen our understanding of the universe and our potential neighbors. The potential discovery of extraterrestrial life raises profound ethical considerations that touch upon our understanding of life itself and our place in the universe. First and foremost, we must grapple with the moral implications of how we interact with these newly found beings, should they exist. Would we treat them with the same respect as we do other forms of life on Earth? It invites a re-examination of our ethical frameworks, pushing us to consider whether extraterrestrial life, regardless of its intelligence or complexity, deserves rights or protection. Furthermore, there's the question of how revealing our discovery to the public could affect humanity. Imagine if we suddenly learned we are not alone in the universe. This monumental change might challenge our beliefs, relationships, and even cultural narratives. The impact on religion, philosophy, and even politics could be immense, as communities may react with fear, excitement, or skepticism. Ethical considerations might arise regarding the timing and manner in which information about extraterrestrial life is disclosed. Additionally, we must consider potential consequences for the extraterrestrial beings themselves. If they possess intelligence, we might face a dilemma about exploitation or intervention. This is especially pertinent in light of historical events on our own planet, where encounters between different cultures have often led to the domination of one by another. Should we seek to communicate and collaborate with them, or would it be more appropriate to leave them undisturbed? These questions echo the significance of our responsibilities as a species and how we would navigate this newfound relationship. The prospect of extraterrestrial contact also urges us to reflect on our environmental ethics. Would our desire to explore or exploit other worlds impact our responsibility to protect our own? By grappling with these ethical considerations, we not only prepare for the possibility of discovering extraterrestrial life, but also learn more about ourselves and our values here on Earth. The universe is a vast and mysterious place, and the key to our understanding may revolve around how we choose to approach the unknown. Gamma-ray bursts are among the universe's most powerful and enigmatic phenomena. These brief but intense flashes of gamma radiation arise from cataclysmic events such as the collapse of massive stars into black holes or the merger of neutron stars. Their significance extends beyond their extraordinary energy. They serve as crucial beacons for understanding the fundamental processes of the universe. One important aspect of gamma-ray bursts is their role in the study of cosmic history. When a gamma-ray burst occurs, it releases energy equivalent to that of billions of suns exploding simultaneously, often outshining entire galaxies. Their light travels vast distances, allowing astronomers to observe these events from billions of light years away, providing a glimpse into the state of the universe shortly after the Big Bang. By studying these bursts, scientists gain insights into the evolution of the universe and the formation of celestial structures. Moreover, gamma-ray bursts are invaluable for understanding the life cycle of stars. The conditions surrounding these bursts reveal details about the processes that lead to the death of massive stars, which play a pivotal role in enriching the cosmos with heavy elements. These elements are essential for the formation of planets and ultimately life as we know it. The study of gamma-ray bursts can thus illuminate the links between stellar deaths and the development of complex cosmic structures. Additionally, gamma-ray bursts are linked to the study of dark matter and energy. The extreme environments in which these bursts occur may provide clues to the fundamental forces shaping our universe. By exploring their characteristics, scientists hope to unravel some of the lingering mysteries of cosmic evolution, helping to piece together the intricate tapestry of the cosmos and our place within it. Fast radio bursts, often referred to as FRBs, are enigmatic phenomena that have puzzled astronomers since their discovery in the early 21st century. These brief flashes of radio waves can last just milliseconds, but can release as much energy as the sun does in several days. Their transient nature and immense energy make them captivating subjects for study, but their origins and mechanisms remain largely unsolved. One reason FRBs are so mysterious is that they are incredibly rare. While their brief appearances can be detected by radio telescopes, the vastness of the universe means that catching these bursts is akin to finding a needle in a cosmic haystack. With only a handful of them carefully mapped out, scientists grapple with the challenge of pinpointing their sources among the billions of galaxies scattered across the cosmos. The uncertainty about whether these bursts are one-off events or part of a repeating pattern adds another layer of complexity. Adding to the intrigue, the search for answers is complicated by the diverse range of potential explanations. Some scientists speculate that these bursts could emerge from highly magnetized neutron stars known as magnetars. Others propose that they might be linked to cataclysmic events like supernovae or even distant galaxies undergoing massive energy releases. Each of these hypotheses opens doors to new questions, but the lack of definitive evidence means the mystery continues to loom large. Furthermore, the impact of FRBs is expanding as researchers have detected repeating signals, hinting at a more complex nature than initially thought. This raises a myriad of questions about their purpose and what they can teach us about the universe's evolution. With advancements in technology and further study, scientists hope to decode the secrets of these rapid bursts of energy, potentially unveiling new aspects of cosmic physics and the nature of our universe. The journey to understand fast radio bursts remains one of the most exciting frontiers in modern astronomy. Auroras, those stunning natural light displays in the polar regions, are more than just a beautiful spectacle. They are windows into the complex interactions between a planet's magnetic field and solar wind. When charged particles from the sun collide with a planet's atmosphere, they get funneled toward the poles by the magnetic field lines. This interaction can create striking visual effects as those particles excite oxygen and nitrogen molecules in the atmosphere, producing radiant colors that dance across the sky. Studying auroras allows scientists to gain insights into the strength and structure of a planet's magnetic field. For example, the intensity and patterns of auroras can reveal how the magnetic field protects a planet from solar radiation. Earth's magnetic field acts as a shield, diverting harmful solar winds, while variations in auroral activity can indicate changes in both solar output and the geomagnetic conditions in space. By analyzing these patterns, scientists can better understand the dynamics of our own planet's magnetic shield and compare it to the magnetic fields on other planets. The study of auroras also provides a unique opportunity to explore the nature of solar interactions in other celestial bodies. For instance, researchers have observed spectacular auroras on Jupiter and Saturn, which exhibit captivating colors and fiercer storms than those on Earth. These observations indicate that strong magnetic fields and fast-moving solar winds can lead to more intense auroral displays, allowing us to infer the strength of those planets' magnetic fields and their atmospheric compositions. Ultimately, auroras serve as a cosmic signaling system that reveals how a planet interacts with solar energy. By examining these vibrant phenomena, scientists continue to unlock the mysteries of our solar system, enhancing our understanding of magnetic fields, atmospheric processes, and the broader implications for planetary habitability. Solar flares and coronal mass ejections are two of the most dramatic phenomena occurring on the Sun, and they can have significant impacts on our solar system. A solar flare is a sudden explosion of energy on the Sun's surface that emits intense bursts of radiation across the electromagnetic spectrum. This radiation can disrupt radio communications on Earth and can even pose a risk to astronauts in space. Coronal mass ejections, often abbreviated as CMEs, are larger and more expansive than solar flares. These massive clouds of charged particles ejected from the Sun can travel through space at incredible speeds, sometimes exceeding 1 million miles per hour. When a CME reaches Earth, it can trigger geomagnetic storms by interacting with our planet's magnetic field. These storms can lead to stunning auroras in the polar regions, but can also disrupt electrical grids and satellite operations, showing just how interconnected our technology is with cosmic events. The influence of solar activity extends beyond Earth. For other planets, especially those with thin atmospheres like Mars, the impact of CMEs can be catastrophic. In the past, CMEs have been blamed for stripping away a planet's atmosphere, which can significantly alter its environment over millions of years. This is particularly concerning when we consider future human exploration on Mars, as understanding solar activity becomes crucial for protecting both equipment and potential colonists. Solar flares and coronal mass ejections are powerful reminders of our Sun's influence over the solar system. They not only shape space weather conditions, but also serve as key players in the intricate dance between solar and planetary dynamics. The ongoing study of these phenomena helps scientists better predict their effects, ensuring our ability to protect technology and explore further into the cosmos. Cosmic voids are vast, empty regions in the universe that contain very few galaxies compared to the surrounding areas. Imagine a sponge. The dense parts are the galaxies and clusters of galaxies, while the larger, more open spaces represent the voids. These voids can span tens of millions of light-years, and they make up a significant portion of the universe's structure, accounting for about 80% of its volume. Their existence is not just a curiosity, they significantly inform our understanding of the universe's architecture. These enigmatic regions challenge our understanding of how matter is distributed in the cosmos. For a long time, scientists believed that matter was evenly spread throughout the universe. However, the presence of these massive voids suggests that space is much more complex than a simple uniform distribution. They raise questions about the processes governing galaxy formation and evolution, forcing astrophysicists to confront why certain regions of space are so sparsely populated. Furthermore, cosmic voids also play a crucial role in our understanding of dark energy. As the universe expands, galaxies in denser regions continue to cluster together, while voids appear to grow larger. Observing the dynamics within these vast emptiness allows scientists to gather insights into the universe's expansion rate. Void behavior suggests that not all areas of the universe respond in the same way to dark energy, which is a critical piece of the puzzle when rethinking the cosmos. Intriguingly, voids can also influence the cosmic microwave background radiation, the afterglow of the Big Bang. Their gravitational effects can cause slight alterations in the patterns of this radiation, providing another tool for cosmologists to understand the universe's origins. So, while cosmic voids may seem like nothingness, they are, in fact, filled with profound implications that continue to refine our knowledge of the universe's grand tapestry. Gravitational lensing is a fascinating phenomenon that occurs when a massive object, like a galaxy or a cluster of galaxies, bends the light from a more distant object, such as a galaxy or a quasar. This bending of light is a consequence of Einstein's general theory of relativity, which tells us that mass can warp and curve spacetime around it. Astronomers have utilized this natural cosmic lens to unlock secrets about the universe, allowing them to study objects that would otherwise be hidden from view. To interpret gravitational lensing, astronomers begin by identifying the distorted images formed by this effect. Often, the more distant light source appears as multiple images, arcs, or even complete ring structures around the foreground object. These distortions provide clues about the mass and distribution of the foreground lensing object. Astronomers apply complex mathematical models to understand how the light is bent and to piece together the three-dimensional structure of the lensing mass. By understanding this modeling, scientists can infer the distribution of dark matter, which does not emit light but has a significant gravitational effect on its surroundings. In addition to mapping the distribution of mass, gravitational lensing serves as a tool for measuring the expansion of the universe. By studying the light from distant galaxies through lensing, astronomers can track how light travels over vast distances, providing insights into the rate at which the universe is expanding and helping to refine key measurements like the Hubble constant. This application makes gravitational lensing indispensable for cosmology, as it bridges our understanding of both the small-scale structures and the vast cosmos. Thus, gravitational lensing is more than just a visual spectacle. It represents a critical observational method in astrophysics. Through detailed analysis, astronomers can explore the invisible realms of dark matter, delve into the dynamics of galaxy formation, and even probe the fundamental nature of the universe itself. The next time we gaze at a galaxy far away, we might just appreciate the hidden stories revealed by the cosmic web of gravitational lensing. Cosmic rays are among the universe's most intriguing phenomena, offering a window into the energetic processes at play in our cosmos. These high-energy particles, primarily protons, travel through space at nearly the speed of light, and when they collide with atoms in the Earth's atmosphere, they produce showers of secondary particles, which we can detect. The origins of these cosmic rays point to some of the universe's most violent environments, such as supernova explosions, neutron stars, and even active galactic nuclei. One of the mysteries surrounding cosmic rays is their acceleration. Understanding how these particles gain such immense energy remains a challenge. Scientists propose that mechanisms like shock waves from supernovae or magnetic fields around neutron stars contribute to the acceleration process. These environments convert kinetic energy into higher forms, making cosmic rays some of the most energetic particles in the universe. As researchers study these mysterious particles, they gather clues about the conditions and processes occurring in these extreme cosmic environments. Another compelling aspect of cosmic rays is their role in shaping our understanding of dark matter and dark energy. While these particles originate from known sources, some of them appear to travel from vast distances, leading scientists to theorize that they could be influenced by regions of space filled with dark matter. This connection could provide critical insights into the composition of the universe and its evolution. As cosmic rays interact with matter, they offer indirect evidence that could help unravel the nature of these elusive cosmic components. The study of cosmic rays encompasses not just the particles themselves, but also the extraordinary events that create them. Each cosmic ray provides a hint, a glimmer of knowledge that points to the underlying mechanics of our universe's energetic processes. As researchers continue to explore their origins, nature, and impact, cosmic rays may uncover greater mysteries of the cosmos, enriching our understanding of space and time. The solar wind is a continuous stream of charged particles released from the outer layers of the Sun, primarily protons and electrons. This flow of particles travels across the solar system at speeds of up to 1 million miles per hour, carrying with it the Sun's magnetic field. As these particles interact with planetary atmospheres, magnetic fields, and bodies in space, they play a significant role in shaping space weather and influencing the environments of various planets. For planets that possess magnetic fields, like Earth, the solar wind is mostly deflected, creating a protective barrier. This magnetic field forms a shield against the charged particles, preventing them from stripping away the atmosphere. However, when this solar wind intensity increases, such as during solar flares or coronal mass ejections, it can cause disruptions. These events can lead to geomagnetic storms, which can affect satellites, navigation systems, and power grids, highlighting the delicate balance between celestial forces and human technology. On planets without significant magnetic fields, like Mars, the solar wind can have far more destructive consequences. Mars, for example, has been stripped of much of its atmosphere because it lacks a strong magnetic shield. Over time, the relentless barrage of solar wind has caused water vapor and other elements to escape into space, significantly affecting the planet's climate and surface conditions. Consequently, understanding the solar wind is critical for comprehension of not only current planetary environments, but also their historical evolution. The impact of the solar wind extends beyond our immediate solar neighborhood. It shapes the conditions across the heliosphere, the vast region dominated by the sun's influence. In this realm, the interactions between the solar wind and the interstellar medium can create complex astrophysical phenomena, from vibrant auroras on polar regions of planets to stunning cosmic landscapes. Thus, the solar wind is not merely a byproduct of solar activity, it is a dynamic force that continuously molds our solar system's environment. Superclusters are colossal formations in the cosmos, representing some of the largest structures known to exist in the universe. These massive groupings of galaxies are made up of interconnected clusters which themselves are composed of hundreds or thousands of galaxies. To put it in perspective, a supercluster can often span hundreds of millions of light-years across. Their sheer size and distribution play a crucial role in shaping the large-scale structure of the universe, influencing the cosmic web of matter that we observe on the grandest scales. The structure of superclusters is not random. Rather, it reflects the underlying gravitational forces at play. Gravity draws matter into these regions, which causes galaxies to cluster together. As superclusters form, they create gravitational wells that not only hold their member galaxies, but also affect nearby regions, pulling in surrounding matter and shaping the very fabric of the universe. This clustering creates a vast web-like structure, filled with voids and filaments, where galaxies and clusters are strung along highways of dark matter. Understanding superclusters provides essential insights into the overall distribution of matter and energy in the universe. Observations show that these formations are not uniformly spread. They tend to cluster more densely in certain areas, which can offer clues about the universe's composition and fate. For instance, by studying the movement and interactions of galaxies within superclusters, scientists can gain valuable information about dark energy, which is believed to drive the accelerated expansion of the universe. Moreover, superclusters can influence star formation rates and the evolution of galaxies. The gravitational pull from nearby galaxies can lead to interactions and mergers, changing the characteristics of the galaxies involved. As researchers delve deeper into the structure and dynamics of superclusters, they reveal the complex interactions that govern the cosmos, providing a window into the universe's past and hints about its future. Scientists use a variety of methods to simulate cosmic events, allowing them to explore and understand the intricate processes that govern the universe. One of the primary tools in this endeavor is computer modeling. By creating sophisticated simulations, researchers can replicate conditions such as the formation of galaxies, the behavior of black holes, or the dynamics of cosmic collisions. These models take into account numerous variables and physical laws, enabling scientists to visualize scenarios that are often impossible or impractical to observe directly. Moreover, scientists employ numerical simulations that rely on large-scale computing power. These simulations can analyze vast amounts of data related to cosmic phenomena. For instance, astrophysicists use supercomputers to model the evolution of the universe, studying how matter clusters and interacts over billions of years. Such simulations help in understanding everything from the Big Bang to the detailed structures of the cosmos we observe today, such as galaxy clusters and dark matter distribution. In addition to computer simulations, scientists sometimes recreate cosmic events in laboratory conditions. This can involve high-energy particle colliders, where they can mimic the extreme conditions of the early universe shortly after the Big Bang. Experiments at facilities like the Large Hadron Collider allow researchers to investigate fundamental particles and forces. These controlled environments provide insights into how matter behaves under extreme conditions, shedding light on processes that occur throughout the universe. Lastly, observational astronomy is a crucial complement to these simulations. By studying celestial phenomena such as the aftermath of supernova explosions or the merging of neutron stars, scientists can validate their models against real-world observations. This combination of simulation, experimentation, and observation creates a comprehensive understanding of cosmic events, continuously refining our knowledge of the universe and its complex workings. The multiverse theory suggests that our universe is just one of many, possibly infinite universes that exist simultaneously. According to this theory, these universes may have different physical laws, constants, and even dimensions. The concept challenges the traditional view of reality, which has primarily focused on a single universe that originated from the Big Bang. Instead, it invites us to imagine a sprawling collection of universes with their own unique properties. Several scientific hypotheses lay the groundwork for the multiverse theory. One key idea comes from quantum mechanics, particularly the concept of quantum superposition, which implies that every possible outcome of a quantum event can occur in its own separate universe. This means that when a decision is made at a quantum level, instead of just one outcome, all potential outcomes occur, each in its own universe. This aspect of quantum theory opens the door to envisioning realities that branch off from one another. Another strand is drawn from cosmology, particularly inflation theory, which suggests that shortly after the Big Bang, the universe underwent a rapid expansion that could have produced bubble-like structures. Each bubble could represent a distinct universe, complete with its specific characteristics. This scenario paints a picture of a constantly inflating cosmic landscape, where new universes are continually emerging and diverging. The implications of the multiverse theory are vast and mind-bending. If multiple universes exist, it raises fascinating questions about the nature of reality, existence, and even the possibility of other forms of life beyond our understanding. While the multiverse remains a controversial and hotly debated topic in the scientific community, it captivates our imagination and challenges our understanding of the cosmos in profound ways. The concept of parallel universes, often referred to as the multiverse theory, has emerged as a fascinating topic within both scientific discussions and popular culture. At its core, the theory posits that there are multiple, perhaps infinite, universes existing alongside our own. These universes may follow different physical laws, contain alternate versions of ourselves, or explore outcomes that diverged from specific moments in our history. This concept provides a unique lens through which scientists can examine the principles of quantum mechanics, particularly when considering the behavior of particles and their interactions at microscopic levels. In the scientific realm, parallel universe theory has profound implications. It challenges our understanding of reality and forces researchers to consider scenarios that might seem beyond the limits of our observable universe. For instance, physicists are intrigued by the idea that every decision made could lead to the creation of a new universe, where different choices result in entirely different outcomes. This not only expands theoretical frameworks, but also opens avenues for exploring the fundamental nature of time, space, and existence itself. Meanwhile, popular culture has eagerly embraced the idea of parallel universes, integrating it into storytelling across various media. Television shows, films, and literature have explored these concepts, allowing audiences to encounter alternative realities, character duplicates, and time travel with a fresh perspective. Classic examples include iconic series like Doctor Who and animated films like Spider-Man Into the Spider-Verse. Such narratives captivate viewers by not only entertaining them, but also inviting them to ponder deeper questions about identity and destiny. Ultimately, the dialogue between science and popular culture around parallel universes enriches our understanding of the cosmos and our place within it. This intersection fosters a broader fascination with scientific principles while allowing audiences to engage with complex theories in creative ways. Whether through rigorous scientific exploration or imaginative storytelling, the allure of the multiverse invites us to envision possibilities that stretch the boundaries of our known universe. Wormholes are fascinating theoretical passages through space-time, connecting two distant points in the universe. Imagine them as tunnels that create shortcuts between different regions of space and, potentially, different times. The concept initially emerged from the equations of general relativity, formulated by Albert Einstein in the early 20th century. In these equations, the fabric of space-time can bend and stretch, suggesting that under certain conditions, a bridge could form between separate areas in space. What makes wormholes particularly intriguing is their implication for time travel. If a wormhole exists and one end is moved at relativistic speeds or placed in a strong gravitational field, time could pass differently at each entry point. This discrepancy opens the door to the potential for traveling backwards or forwards in time. A traveler entering one end could emerge in a different time period, having traversed both space and time within moments. While this idea captivates the imagination and has been a popular subject in science fiction, it also comes with a multitude of scientific challenges. One of the challenges is the stability of these hypothetical structures. Most solutions suggest that a wormhole would require a form of exotic matter with negative energy density to remain open. This exotic matter is purely theoretical at this point. It has not yet been discovered. Furthermore, even if wormholes did exist, numerous questions arise about causality and the potential paradoxes of altering history, which would dramatically complicate the notion of time travel. Despite these hurdles, the study of wormholes and their implications continues to inspire scientists and theorists alike. They serve as a captivating reminder of the mysteries that lie at the edge of our understanding of the universe. As researchers delve deeper into the realms of quantum physics and relativity, the tantalizing possibility of wormholes may one day reveal new truths about the nature of space, time, and perhaps even our understanding of reality itself. The holographic principle is a fascinating idea that suggests the entire universe can be described by information encoded on a distant surface or boundary. Imagine the cosmos as a three-dimensional hologram, where the actual details of our three-dimensional reality are merely projections of information stored in a lower-dimensional format. This shifts our perspective on space and time, prompting profound questions about the nature of reality itself. If true, the holographic principle could bridge the realms of quantum physics and gravity, offering insights into the mysteries of black holes and the fabric of space-time. Traditional physics often treats space and time as separate entities, but this principle encourages us to rethink that division. It hints that rather than being fundamental, dimensions may arise from deeper, more basic interactions of information. This opens the door to revolutionary theories about how everything in the universe connects, intertwining microcosmic particles with the vast macrocosm. Furthermore, this principle might reshape our understanding of consciousness and perception. If our reality is a projection, then the way we experience the world could be a reflection of deeper, non-physical information. This connection to information could pave the way for new insights into the nature of human perception, consciousness, and even the limits of what we can know about the universe. Essentially, this principle may suggest that the universe is more like a grand computer code than a concrete structure. The implications of the holographic principle extend far beyond theoretical physics. It invigorates discussions in philosophy, consciousness studies, and even spirituality. By proposing that our lived reality can stem from simpler, encoded information, It invites us to explore fundamental questions about existence, purpose, and our relationship to the cosmos. If we are living in a holographic reality, understanding this principle could indeed revolutionize not just science, but the very way we perceive our place in the universe. Quantum foam is a compelling concept in theoretical physics that attempts to describe the very fabric of the universe at the smallest scales. It is proposed to exist at the Planck scale, which is about 100 billion times smaller than an atom. At this minute scale, the smooth fabric of spacetime breaks down into a tumultuous, frothy structure akin to bubbles in a foamy liquid. This foamy essence of spacetime reflects the effects of quantum fluctuations, where particles and energy briefly pop in and out of existence. The significance of quantum foam lies in its potential implications for our understanding of gravity and the fundamental forces of nature. In Einstein's theory of general relativity, spacetime is treated as a smooth continuum. However, quantum foam suggests that at extremely small scales, this smoothness is disrupted, leading to a more complex and chaotic structure. This could illuminate how gravity operates in the quantum realm, which is a key puzzle in physics, as we currently lack a complete theory that combines gravity with quantum mechanics. Moreover, quantum foam raises intriguing questions about the nature of reality itself. It hints that what we perceive as solid objects and stable forces may actually result from a much more dynamic and fluctuating foundational level of space-time. This challenges our perceptions and suggests that the universe is far more complex than we observe in everyday life. Studying quantum foam could provide insights into the unification of quantum mechanics and general relativity, potentially paving the way for groundbreaking discoveries in theoretical physics. In recent years, researchers have begun to explore ways to empirically test these ideas, though it remains a formidable challenge. Experiments aimed at probing the effects of quantum foam might reveal whether its existence can be measured, shedding light on the very origins of the universe and the forces that govern it. The pursuit of understanding such concepts underscores the remarkable journey of science as we strive to decode the mysteries of our universe. Warp drive technology has captured the imagination of scientists and science fiction enthusiasts alike. At its core, this concept proposes the ability to travel faster than light, effectively bending or warping the fabric of spacetime itself. The fundamental idea is that instead of moving through space, a spacecraft would manipulate the space around it, creating a bubble that propels the ship forward without violating the laws of physics as we currently understand them. Researchers draw inspiration from Einstein's theory of relativity, which posits that as an object approaches the speed of light, its mass becomes infinitely large, requiring infinite energy to accelerate further. Warp drive offers an ingenious workaround by suggesting that the spacecraft could expand space behind it and contract space in front of it. This would theoretically allow for significant cosmic distances to be traversed in a fraction of the time it would normally take. Concepts like the Alcubierre drive illustrate this possibility, making it a focal point of theoretical exploration in modern physics. Although warp drive remains firmly in the realm of theoretical physics, recent advancements in our understanding of quantum mechanics and cosmic structures could provide insights into making it a reality. Some scientists are investigating the energy conditions necessary for such technology, including the endeavor to create negative energy density to facilitate the warp bubble. While this may sound far-fetched, the exploration of these concepts not only enhances our understanding of the universe, but also drives innovation in propulsion technologies. Importantly, the potential implications of warp drive extend beyond mere speed. It raises profound questions about interstellar colonization, the nature of time, and humanity's place in the universe. As we continue to explore the possibilities of warp drive, scientists remind us that we are only at the beginning of this journey, with many challenges ahead. Yet, each step taken on this path could one day transform how we approach space exploration, opening up new horizons and redefining our relationship with the cosmos. Chaos theory, at its core, explores how tiny variations in initial conditions can lead to vastly different outcomes in complex systems. In the cosmos, this concept holds profound significance, particularly when examining cosmic events like the formation of galaxies or the behavior of celestial bodies over time. For instance, even a slight variation in the position or speed of a star can create a ripple effect that influences the trajectory of surrounding stars, leading to unpredictable paths and formations. When we look at the universe, it is filled with intricate structures, from spiral galaxies to clusters of stars shaped by gravity and various forces. These structures emerge from chaos, the gravitational interactions between countless particles, dust, and gas create patterns that might seem orderly, but are inherently unpredictable when scrutinized at a fundamental level. A classic example is the formation of star clusters. Despite starting with similar conditions, the eventual outcomes can vary tremendously due to minor differences in their early states, highlighting the sensitivity to initial conditions that chaos theory emphasizes. Astrophysicists apply chaos theory to model cosmic phenomena like the movements of planets and the interactions of galaxies. These models reveal that small changes can lead to entirely different scenarios in the life cycle of stars and the collision of galaxies. For instance, the collision dynamics of two galaxies can display chaotic behavior, resulting in various outcomes like the formation of new stars or the ejection of stars into intergalactic space. Such insights help scientists understand not just the structure of the universe, but also its evolution over billions of years. Chaos theory provides a rich framework for comprehending the complex and often unpredictable nature of cosmic events. By recognizing the delicate interplay of forces and initial conditions, scientists can better understand the stunning variety of structures and phenomena that populate our universe, from the smallest planets to sprawling galaxy clusters. This dynamic nature of the cosmos continues to fascinate, reminding us that even within the vastness of space, there remains a thread of both order and chaos that defines our reality. The concept of artificial wormholes is one of the most intriguing ideas within the realm of theoretical physics and cosmology. A wormhole is a shortcut through space-time that could connect two distant points in the universe or even different universes entirely. Theoretical physicists have often posited that if we could create such structures, the possibilities for faster-than-light travel and instantaneous communication across vast cosmic distances could open up remarkable new horizons. Imagine traveling across galaxies in mere moments, or sending signals to the far reaches of space without the delays imposed by light speed constraints. However, the journey toward creating artificial wormholes is fraught with significant challenges. Firstly, the exotic matter required to stabilize a wormhole and keep it open is purely theoretical at this point. This exotic matter would possess negative energy density, a concept that stretches our current understanding of physics. Without it, any wormhole created may collapse under its own gravity before anything could pass through. The search for this elusive material is one of the many hurdles scientists face. Moreover, even if a stable wormhole could be artificially created, the implications of its use raise numerous questions. What would happen to objects entering a wormhole? Could they be harmed, or would they emerge intact? Furthermore, if wormholes could be used for travel, the risks of paradoxes and unforeseen consequences loom large. For instance, the potential for time travel through these shortcuts could lead to situations where cause and effect become entangled in perplexing ways, leading to paradoxes that scientists are still trying to understand. Despite these challenges, the mere pursuit of artificial wormholes encourages innovative exploration in physics and cosmology. Researching these possibilities not only enhances our understanding of the universe, but also pushes the boundaries of what is scientifically possible. As we continue to uncover the mysteries surrounding space-time and its properties, who knows? Perhaps one day the dream of traversing the stars through artificial wormholes will become a reality, intertwining science fiction with the fabric of our understanding of the cosmos. The concept of time loops, once relegated to the realm of science fiction, has gained traction in theoretical physics as our understanding of the universe evolves. These fascinating possibilities arise from the very fabric of space-time, as predicted by Einstein's theory of relativity. In this framework, time is not a constant flow. Rather, it can bend and twist under the influence of gravity and velocity. Recent advances in theoretical physics have prompted scientists to explore scenarios where time may be revisitable through what we know as closed time-like curves. In these discussions, physicists examine conditions under which someone could travel back to an earlier point in their own life or alter events in the past. The implications are profound, raising questions about causality and the nature of reality itself. Proposals often rely on exotic matter or hypothetical constructs, such as wormholes, which are theoretical passages through space-time, allowing for shortcuts between different points in time and space. The idea is tantalizing, but it poses significant challenges and paradoxes that scientists labor to resolve, like the famous grandfather paradox, where one could potentially prevent their own existence. Alongside these theoretical explorations, findings in quantum mechanics also contribute to the intrigue surrounding time loops. Some interpretations suggest that particles can exhibit behaviors that challenge our traditional understanding of time, leading to phenomena such as entanglement, which suggests a connection that seems to defy the limits of space and time. This entwining of events hints at a deeper layer of reality where time may not be linear or absolute. Overall, advances in theoretical physics continue to provoke thought around time loops, inviting researchers to contemplate a universe where the past and future might be more interconnected than we can comprehend. As we delve deeper into the mysteries of the cosmos, these ideas not only broaden our understanding of time, but also inspire intriguing conversations about the nature of existence, reality, and the very laws that govern our universe. The concept of dark flow introduces an intriguing layer to our understanding of cosmic motion. It suggests that our universe, despite its vastness and apparent randomness, is influenced by unseen forces acting on galactic clusters. Observations made by astronomers suggest that certain galaxy groups, specifically those in the observable universe, are not just moving due to the expansion associated with the Big Bang. Instead, they seem to be moving in a particular direction, hinting at a greater gravitational source beyond the visible universe. This phenomenon challenges the prevailing notion that the cosmos is isotropic and homogeneous on a large scale. In simpler terms, isotropic means that the universe looks the same in all directions, and homogeneous means it has a uniform distribution of matter. The existence of dark flow implies that there are larger structures or masses, perhaps beyond the observable limits of our universe, that exert a gravitational influence, causing these galaxies to drift towards them. Such a notion raises questions about the overall structure of the universe and what lies beyond the sections we can observe. Moreover, dark flow could hint at the presence of vast superclusters or even other universes within a multiverse framework. The idea that we might be affected by cosmic entities we cannot see or understand rewrites parts of our cosmic narrative. This perspective challenges scientists to rethink gravitational dynamics and cosmic topology. As they delve deeper into these patterns, they are examining the implications of a universe that may not be as simple or straightforward as once thought. Ultimately, the concept of dark flow invites us to appreciate the complexities and mysteries still embedded in the fabric of our universe. As researchers continue to gather evidence and analyze cosmic data, our understanding of cosmic motion may evolve, revealing the universe as a more interconnected and layered environment. This ongoing investigation into dark flow is a testament to the ever-expanding horizons of cosmological knowledge, keeping the quest for understanding both relevant and exciting. Advancements in telescope technology are fundamentally transforming our understanding of the universe by allowing us to peer deeper into space than ever before. The evolution from simple optical telescopes to sophisticated instruments like radio telescopes and space-based observatories has unlocked secrets of the cosmos that were once beyond our reach. These innovations enhance our ability to capture more light, observe a wider range of wavelengths, and provide sharper images, expanding our cosmic horizons substantially. For instance, the Hubble Space Telescope, launched over 30 years ago, has pioneered many discoveries, capturing breathtaking images of distant galaxies and nebulae. Its ability to detect ultraviolet and infrared light enables scientists to observe celestial phenomena that are invisible to the naked eye. More recently, the James Webb Space Telescope has taken this capability even further. Positioned far away from Earth to avoid atmospheric interference, Webb's infrared vision allows us to look back in time to witness objects formed just after the Big Bang, offering insights into the early universe and the formation of stars and galaxies. Another significant advancement comes from radio telescopes, like the ones in the Very Large Array in New Mexico. These massive antennas work together to observe cosmic phenomena that emit radio waves, such as pulsars and cosmic microwave background radiation. The data gathered from these instruments help researchers piece together the puzzle of cosmic evolution, including the expansion of the universe and the nature of dark matter and dark energy. As technology continues to advance, upcoming projects aim to enhance our observational capabilities even further. Initiatives like the Square Kilometre Array, which will be built in South Africa and Australia, promise to revolutionize our understanding of the universe by providing unprecedented sensitivity and resolution. By leveraging these cutting-edge technologies, we are not just expanding our cosmic horizons, we are rewriting the story of the universe itself, one discovery at a time. Space probes are pivotal for advancing our understanding of deep space, functioning as our eyes and ears in the cosmos. These unmanned spacecraft are designed to travel beyond the Earth's atmosphere, conducting scientific investigations in regions of space that are unreachable by humans. Equipped with specialized instruments, they gather invaluable data about distant celestial bodies, dive into the atmosphere of gas giants, and even collect samples from asteroids and comets. The hope is to unveil the mysteries of our solar system and beyond. As we journey deeper into space, probes serve a multitude of roles. They help map surfaces and analyze atmospheric compositions, providing insights into the weather patterns of planets like Mars, the gas giants, and their moons. Some missions, like the Mars rovers, rely on advanced technologies to examine soil and rock samples for signs of past or present life. Meanwhile, probes like New Horizons have traversed the icy realm of Pluto and continue to relay secrets about the Kuiper Belt, a less explored area at the edge of our solar system. Looking toward the future, space probes are expected to become even more sophisticated. With advancements in artificial intelligence, these missions can make real-time decisions, adapting to unforeseen circumstances as they explore. Upcoming missions, such as those targeting Europa, one of Jupiter's moons, will examine subsurface oceans that could harbor life. These explorations could potentially reshape our understanding of habitability across the universe. As we push the boundaries of our knowledge and technology, space probes will play a critical role in uncovering the secrets of deep space. They not only bring back fascinating data, but also inspire future generations of scientists and explorers. With each mission, we move one step closer to understanding our place in the vast expanse of the universe. Space missions are pivotal in our quest to understand the universe and its many mysteries. By sending sophisticated instruments into space, scientists can gather data from celestial bodies and phenomena that are impossible to study in detail from Earth. This is due to atmospheric interference and the limitations of ground-based telescopes, which can be hindered by weather and light pollution. Space missions enable us to explore environments that are extreme or incredibly distant, enhancing our knowledge of the cosmos. One of the most significant advantages of space missions is their ability to carry advanced tools and instruments designed explicitly to detect various forms of radiation and signals from space. For example, telescopes positioned outside Earth's atmosphere can capture clear images of distant galaxies, nebulas, and other celestial entities. These observations help scientists piece together the history of the universe, including the formation and evolution of stars and galaxies over billions of years. Additionally, robotic spacecraft and landers provide direct exploration of planets and moons in our solar system. Missions to Mars, such as the Perseverance rover, gather samples and analyze soil and rock compositions, seeking signs of past life and clues about the planet's climatic history. Saturn's moon Enceladus, explored by the Cassini spacecraft, unveiled geysers that spew water vapor, hinting at subsurface oceans and potential habitability. Such discoveries prompt new questions about the origins of life and the conditions that may support it beyond Earth. Furthermore, space missions extend our reach beyond our solar system, probing the mysteries of phenomena like exoplanets and gravitational waves. Missions such as the Kepler Space Telescope have revolutionized our understanding of planets orbiting other stars by identifying thousands of these worlds. Each mission contributes to a greater tapestry of knowledge, fostering a deeper appreciation for the wonders of the universe and motivating us to explore further. The complex nature of these celestial phenomena unravels slowly, yet each discovery breeds excitement and anticipation for what lies ahead in our cosmic exploration. The prospect of human colonization of other planets is no longer the stuff of science fiction. It's becoming an increasingly tangible goal for scientists and visionaries alike. In the near future, we might witness the first steps toward establishing permanent human settlements on places like Mars or the Moon. This endeavor may start with small, self-sustaining habitats where astronauts conduct research, test technologies, and develop the methods needed for larger populations. These initial habitats will likely be built using materials sourced from the planet itself, a process known as in situ resource utilization. By utilizing local resources, we can reduce the need to transport everything from Earth, which is both costly and logistically challenging. Imagine habitats constructed from Martian regolith, the powdery soil covering the surface. This innovation would not only support sustainable living, but also lay the groundwork for expansive colonies over time. As technology evolves, we may see advancements in life support systems, capable of recycling air and water with incredible efficiency. This will be crucial for long-term habitation. In addition, the cultivation of crops in controlled environments could enable settlers to produce their own food, marking a significant shift from reliance on Earth supplies. With robust bioregenerative systems, colonies could thrive, growing a new agricultural ecosystem in the barren landscapes of other worlds. However, colonization will bring challenges, including psychological adjustments to life away from Earth and the risks posed by radiation and microgravity. As we learn to adapt to these new environments, the dream of a human presence on other planets inches closer to reality. The journey will not only be about survival, but also about the exploration of what it means to be human in the universe, fostering a spirit of discovery and wonder that resonates with the pioneering spirit of our species. Artificial intelligence is revolutionizing astronomical research in remarkable ways, acting as a powerful tool that enhances our ability to analyze vast amounts of cosmic data. The universe presents an overwhelming array of information, from the countless light waves reaching our telescopes to the intricate patterns of celestial movements. Traditional methods of data analysis have struggled to keep pace with this flood of information. However, AI algorithms excel at sifting through these large datasets, identifying trends and anomalies that might otherwise go unnoticed. One exciting application of artificial intelligence in astronomy is in the field of galaxy classification. Scientists typically categorize galaxies based on their shapes, which requires meticulous observation and considerable time. AI can automate this process by using deep learning techniques. By training algorithms on existing labeled datasets of galaxies, AI can recognize and classify new galaxies within moments, significantly accelerating the pace of discovery. This not only saves time, but also opens up opportunities to explore previously overlooked regions of the cosmos. Another pivotal role AI plays in astronomy is in the analysis of light curves, which track the brightness of objects over time. Such analysis is especially valuable for discovering exoplanets, planets outside our solar system. By using AI to detect subtle changes in brightness caused by planets passing in front of their host stars, researchers can identify new worlds with greater accuracy and efficiency. This technology allows scientists to analyze data from various space missions in ways that were previously unimaginable. Beyond classification and discovery, AI is proving to be instrumental in predicting astronomical phenomena. By integrating AI with simulations of cosmic events, researchers can forecast occurrences such as supernovae or gravitational waves with improved precision. As we continue to deepen our understanding of the universe, it's clear that artificial intelligence is more than just a tool. It is becoming an essential partner in the quest to unlock the mysteries of space, enabling researchers to unveil new insights faster than ever before. As humanity stands on the brink of a new era in space exploration, the prospect of space mining and resource utilization opens up a treasure trove of opportunities, but it also raises profound ethical questions. Among the primary concerns is the potential for exploitation and environmental degradation. Just as Earth has experienced the consequences of resource extraction, such as pollution and habitat destruction, these issues could be replicated on other celestial bodies. How do we ensure that our quest for resources does not lead to similar catastrophic outcomes for places like asteroids or the Moon, environments that have existed unchanged for billions of years? Moreover, there is the issue of ownership and sovereignty. The Outer Space Treaty of 1967, which forms the basis of international space law, states that no nation can claim sovereignty over celestial bodies. However, with the advent of commercial space mining ventures, questions about who has rights to these resources are emerging. If a company mines an asteroid, is the mined material considered property? This dilemma raises significant implications for national interests, international relations, and the future governance of space. Additionally, there is the ethical treatment of potential extraterrestrial life forms. While no definitive evidence of life beyond Earth has been found, should we act as if it may exist? The discovery of microbial life on another planet could complicate our discussions on resource utilization. Extracting resources and contaminating environments where life is present poses moral dilemmas that scientists and policymakers must navigate carefully. Lastly, we cannot overlook the issue of inequality. Space mining has the potential to become a multi-trillion-dollar industry, but access to this frontier will likely reflect existing disparities between wealthy countries and those with fewer resources. How can we ensure that the benefits of space resources are shared equitably? These ethical considerations require robust dialogue among ethicists, scientists, and lawmakers to craft guidelines that reflect our shared responsibility to protect both Earth and our potential neighbors in the cosmos. International collaborations are instrumental in propelling the goals of space exploration forward. Historically, space has been a realm where nations have come together, acknowledging that the challenges and mysteries of the universe transcend borders. By pooling resources, expertise, and funding, countries can undertake ambitious projects that would be unattainable individually. This collective effort enhances scientific research, technology development, and even the sharing of data, resulting in richer and more comprehensive explorations of space. Take the International Space Station, for instance. This remarkable achievement symbolizes global cooperation, with contributions from space agencies across the United States, Russia, Europe, Japan, and Canada. In this microgravity environment, scientists conduct vital experiments that benefit not just space exploration, but also life on Earth. Medical research, materials science, and environmental monitoring are just a few fields that have gained invaluable insights, thanks to this shared platform. Moreover, international collaborations expand access to space for developing nations, allowing them to participate in space activities. As countries like India, Brazil, and South Africa contribute to and benefit from global projects, they bring unique perspectives and innovations to the table. This inclusivity fosters a diverse scientific community focused on solving universal problems, promoting peace and diplomacy through joint exploration endeavors. Finally, these partnerships enable the sharing of ambitious long-term goals, such as Mars colonization or asteroid mining, which require vast investments and multinational teams. By working together, countries can strategize and synergize their efforts, thereby increasing the likelihood of success. It is through these shared missions that humanity moves closer to unlocking the secrets of the cosmos, nurturing not just our understanding of space, but also our shared place within it. The future of space travel is poised for transformative breakthroughs in propulsion technology, which could vastly reduce travel time and expand our reach into the cosmos. One of the most exciting advancements making waves is ion propulsion. Unlike traditional chemical rockets that rely on burning fuel, ion thrusters utilize electricity to accelerate ions, generating thrust. This method is remarkably efficient and allows vehicles to maintain a steady acceleration over long periods, making it ideal for deep space missions. Another promising avenue is the development of nuclear thermal propulsion. This technology involves heating a propellant, such as hydrogen, in a nuclear reactor before expelling it through a rocket nozzle. The potential for higher efficiency and greater thrust means vessels could reach distant destinations like Mars much quicker than using conventional engines. Imagine a journey to the Red Planet, taking only a few weeks instead of several months. This may soon become a reality, fundamentally altering humanity's capacity for interplanetary travel. Further down the road lies the tantalizing prospect of antimatter propulsion. In theory, combining matter with antimatter could release enormous amounts of energy, far surpassing that of chemical rockets. While currently in the realm of theoretical physics and requiring revolutionary breakthroughs to harness, the potential to achieve near-light speeds is an entrancing possibility. Antimatter's energy yield is so vast that even a small amount could propel a spacecraft through the solar system in a fraction of the time we experience today. Lastly, researchers are also exploring solar sails, which harness the sun's radiation pressure to propel spacecraft. Unlike traditional propulsion methods, solar sails require no fuel, relying solely on the power of sunlight. As these developments continue to unfold, we stand on the brink of a new era in space exploration, with each breakthrough redefining our understanding of what is possible and bringing the stars closer than ever before. Space tourism stands at the intersection of adventure and education, offering individuals unique first-hand experiences of the cosmos. As commercial space travel becomes more accessible, it allows ordinary people the chance to view Earth from above, float in microgravity, and witness the vastness of space. Such experiences can profoundly deepen one's understanding of our planet's fragility and the intricate systems that sustain life. Furthermore, when space tourism becomes commonplace, the sheer act of traveling beyond our atmosphere could spark a broader interest in astrophysics, space exploration, and astronomy. People who once felt detached from these fields might become inspired to learn more and engage with them on a deeper level. As tourists share their experiences, whether through social media or public talks, they can foster a new cultural appreciation for space, urging society to prioritize its study and protection. The phenomenon of seeing Earth from the vantage point of space offers a transformative perspective. Many astronauts describe a profound emotional experience known as the overview effect, where the beauty and fragility of our planet take center stage against the backdrop of the universe. This shared phenomenon can inspire positive social and environmental change as people return from their journeys with newfound wisdom about our place in the cosmos. Finally, increased public interest in space tourism could lead to greater support for scientific research and funding for space exploration initiatives. As awareness spreads, individuals might rally behind projects that seek to address the mysteries of the universe, from discovering new planets to understanding the formation of galaxies. This shift could catalyze a generation of explorers dedicated to expanding humanity's reach into the solar system and beyond, propelling us toward a future where space is not just a frontier, but a shared destination for all. Astronomers are continually on the brink of groundbreaking discoveries, ever eager to unravel the secrets of the universe. One of the most pressing questions they seek to address is the enigmatic nature of dark energy. This mysterious force is believed to be responsible for the accelerated expansion of the universe. Understanding its properties and origins could fundamentally change our grasp of cosmic evolution and the ultimate fate of the universe itself. Another significant inquiry involves the existence of life beyond Earth. Scientists are searching for exoplanets in habitable zones where conditions might support life as we know it. Missions like the James Webb Space Telescope aim to study the atmospheres of these distant worlds, looking for signs of biological activity. Discovering even microbial life would not only alter our understanding of biology, but also challenge our philosophical views about humanity's place in the cosmos. The quest to comprehend black holes also continues to captivate astronomers. Recent advancements have allowed us to capture images of black holes and study their effects on surrounding matter. Researchers aim to unlock the mysteries of what occurs inside these cosmic giants and how they influence the evolution of galaxies. Ultimately, understanding black holes may provide insights into the fundamental laws of physics, including how they relate to quantum mechanics and general relativity. Finally, the cosmic microwave background, which is the afterglow of the Big Bang, remains a hot topic for exploration. By analyzing this relic radiation, astronomers hope to glean clues about the early universe, its growth, and the formation of galaxies. Each new revelation in this field has the potential to reshape our models of the cosmos, offering a clearer picture of how our universe came to be and where it is heading next. As technology advances and our observational capabilities expand, these questions will undoubtedly pave the way for future breakthroughs in our understanding of the universe.